Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable, to let the weight of the day finally settle away from your shoulders. Where in the world are you watching from? A quiet bedroom where the stars might be visible through your window? A cozy corner where the hum of the world has finally faded to something manageable? Wherever you are, you're exactly where you need to be. Tonight we're going to explore something that sounds simple but opens into wonder. How long would it actually take to reach every planet in our solar system? We'll discover that the answers depend on far more than just distance, that the universe moves in ways that complicate our journeys, and that even our nearest neighbours require patience measured in months and years. It's a journey that spans our entire cosmic neighbourhood, from Mercury's blistering proximity to Neptune's frozen distance, and along the way we'll understand why getting anywhere in space is so beautifully, impossibly complex. But don't worry, this isn't going to be a rapid-fire countdown of numbers and statistics. Instead, we'll move slowly and carefully through each world, taking our time to understand not just how long the journey takes, but why, what we've learned from the ships we've sent, and what it means for our future among the stars. By the end, I think you'll find that distance in space is stranger and more fascinating than simple miles could ever suggest. If you enjoy these calm explorations of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for returning to these quiet journeys through space and time, so settle in, let your shoulders drop. Take a slow breath and feel your body begin to release the tension it's been holding. And let's begin our slow drift through the solar system, world by world, discovering just how far we really are from everywhere else. There's nowhere you need to be right now, nothing you need to do. Just listen and let the story unfold like the universe itself, vast and patient and full of quiet marvels. When we ask how long it takes to reach another planet, we're asking what seems like a straightforward question. We want a number, a clean answer, something we can hold in our minds. But space, in its gentle way, refuses such simplicity. The truth is more layered, more beautiful, and frankly more strange than any single number could capture. The planets aren't sitting still, waiting for us. They're moving, always moving, each one tracing its own elliptical path around the Sun at its own particular speed. Earth completes its orbit in 365 days. Mercury rushes around in just 88. Neptune takes 164 Earth years to make a single journey around our star. This means the distance between any two planets is constantly changing, expanding and contracting in a cosmic dance that's been going on for 4.5 billion years. When we talk about the distance to Mars, for instance, we might say it's roughly 140 million miles away on average. But that word average conceals enormous variation. At its closest approach, called opposition, Mars can be as near as 33 million miles from Earth. At its farthest, when it's on the opposite side of the Sun from us, it can be as distant as 250 million miles. The difference between these extremes is larger than the distance from the Earth to the Sun. And this brings us to something equally remarkable. We don't fly straight toward our destination. We can't. Both Earth and the target planet are moving, and moving fast. Earth travels through space at about 67,000 miles per hour in its orbit. We have to account for that motion. Any spacecraft we launch inherits Earth's orbital velocity, and then we add more speed to send it on its way. But the trajectory isn't a straight line. It's a curve, an arc that intercepts the orbit of our target planet at precisely the moment the planet arrives at the same point. It's less like throwing a ball at a target and more like throwing a ball to where a moving target will be in the future. This kind of path is called a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who calculated these trajectories in 1925, decades before we had the technology to actually attempt them. It's the most fuel-efficient way to travel between two orbits, using the sun's gravity and the spacecraft's momentum to coast most of the way. But efficiency in fuel means patience in time. These elliptical paths are long, graceful arcs through space. The speed of the spacecraft matters too, of course. Our fastest probes have used gravitational assists, swinging past planets to steal a bit of their orbital momentum, slingshotting themselves to higher speeds. The Parker Solar Probe, designed to study the Sun, has reached speeds of over 430,000 miles per hour relative to the Sun, making it the fastest human-made object ever. But even at such incredible speeds, crossing the solar system takes years. So when someone asks how long it takes to reach Jupiter or Saturn or any other world, the honest answer begins with questions. When are we launching? What trajectory are we taking? How fast is the spacecraft? What technology are we using? Are we trying to orbit, to land, or just to fly past? Each choice changes the answer, and this is part of what makes space travel so profoundly challenging and so endlessly fascinating. There are no simple journeys out there, only careful calculations and patient years, which leads us naturally to consider the closest planet, the one that seems like it should be easiest to reach, and yet presents its own unique and beautiful complications. Mercury is our closest planetary neighbour to the Sun, orbiting at an average distance of just 36 million miles from our star. Earth orbits at 93 million miles. You might think this makes Mercury relatively easy to reach, closer than Venus, closer than Mars. But Mercury is actually one of the hardest planets in the solar system to visit, and the reason why teaches us something fundamental about orbital mechanics. The problem is the Sun itself. Mercury sits deep in the Sun's gravity well, moving at tremendous speed to avoid falling inward. It orbits the Sun at roughly 107,000 miles per hour, compared to Earth's 67,000 miles per hour. To reach Mercury, a spacecraft launched from Earth has to shed an enormous amount of orbital energy. It has to slow down relative to the Sun, falling inward against the natural momentum it inherited from Earth. This is counterintuitive. We think of spaceflight as adding speed, as acceleration and thrust. But to reach Mercury efficiently, we have to brake, to lose velocity, to fall sunward in a controlled descent. And doing so requires either enormous amounts of fuel or enormous amounts of time and clever trajectory planning. NASA's Mariner 10 became the first spacecraft to visit Mercury, flying past it 3 times in 1974 and 75. The journey took nearly 5 months from launch to first flyby, but Mariner 10 didn't go directly. It first flew past Venus, using that planet's gravity to bend its trajectory and slow its orbital speed enough to fall inward to Mercury's orbit. Even then, it could only fly past, not orbit. It didn't have the fuel to slow down enough to be captured by Mercury's weak gravity. It would be 30 years before we sent another mission to Mercury. Messenger, launched in 2004, took a full 6.5 years to reach Mercury orbit. 6.5 years to reach a planet that's closer to the Sun than we are. The spacecraft flew past Earth once, Venus twice, and Mercury itself 3 times before finally entering orbit in 2011. Each flyby adjusted its trajectory, stealing or adding tiny amounts of velocity, spiralling slowly inward until it could match Mercury's blistering orbital speed. The most recent mission, Bepi-Colombo, launched in 2018 and won't arrive at Mercury until 2025. 7 years of flight, using 9 planetary flybys to gradually adjust its path. 1 flyby of Earth, 2 of Venus, and 6 of Mercury itself before final orbit insertion. It's an intricate gravitational ballet choreographed years in advance. If we wanted to reach Mercury faster, we could. We could build a spacecraft with powerful engines and enormous fuel reserves and send it on a more direct path. But the fuel requirements would be staggering. It's far more practical to be patient, to use the gravity of the inner planets as free boosts and brakes, to accept that the journey takes years because years are cheaper than fuel, and there's something beautiful in this patience, in the understanding that the fastest path is not always the straightest. that sometimes falling towards something requires first moving away from it. Mercury sits there in its scorched orbit closest to the fire, and reaching it demands a respect for the fundamental forces that govern motion in space. The Sun's gravity is powerful, and Mercury's speed is unforgiving. We reach it not by fighting these facts, but by working with them, slowly, carefully, over years. Let that thought settle as we turn our attention outward again, to the planet that seems like it should be the easiest to visit, the one that approaches closer to Earth than any other world in the solar system. Venus orbits between Earth and Mercury at an average distance of 67 million miles from the Sun. It's the closest planet to Earth, approaching to within about 25 million miles at its nearest. You can see it with your naked eye, brilliant in the evening or morning sky, brighter than any star. We call it the evening star, the morning star, our celestial twin, and in terms of travel time it lives up to that intimacy. A direct flight to Venus, launched at the right time when the planets are properly aligned, takes about 3.5 to 4 months. Mariner 2, the first successful planetary mission, reached Venus in just 109 days in 1962. More recent missions have taken similar times. The Soviet Venera probes, dozens of them launched over decades, made the journey in about 4 months on average. NASA's Magellan orbiter took just over 15 months, but that was using a slower, more fuel-efficient trajectory. Venus is genuinely close, genuinely accessible. We've sent more missions to Venus than to any other planet except Mars. The Soviets made it a particular focus, landing 10 spacecraft on its surface between 1970 and 1982, an extraordinary achievement given the conditions there. But here's what makes Venus so fascinating and so tragic. Reaching it is relatively easy, but surviving there is almost impossible. The surface of Venus is hot enough to melt lead. The atmospheric pressure is 90 times greater than Earth's, equivalent to being 3,000 feet underwater. The atmosphere is almost entirely carbon dioxide, thick with clouds of sulfuric acid. The Soviet landers, built like deep-sea submarines with titanium hulls, survived on the surface for only minutes to hours before succumbing to the heat and pressure. The longest surviving lander, Venera 13, transmitted data for 127 minutes before failing, just over 2 hours on the surface of our nearest neighbour. This creates a strange asymmetry. Venus is easy to reach but impossible to stay on. It takes 4 months to get there, and you might survive for 2 hours. The return journey, of course, has never been attempted from the surface. No spacecraft has ever returned samples from Venus, though missions are proposed. The engineering challenges are immense, still. There's value in studying Venus from orbit, from flyby, from those brief moments of surface contact. Venus likely began as an Earth-like world, with oceans and perhaps even life. Something went catastrophically wrong in its history. A runaway greenhouse effect boiled the oceans, filled the atmosphere with water vapour and carbon dioxide, and created the hellish environment we see today. Understanding how and why this happened helps us understand our own planet's climate, the delicate balance that keeps Earth habitable, and Venus teaches us something about proximity. Close doesn't mean friendly. The nearest world is toxic, hostile, lethal. We can reach it in a matter of months, but we cannot stay. It's a reminder that distance in space is only one measure of accessibility. Environment matters, survival matters. You can visit a place you cannot inhabit. The trajectory to Venus is straightforward compared to Mercury. We don't fight the Sun's gravity as much. We're essentially moving from one circular orbit to a slightly smaller circular orbit, a relatively modest adjustment in orbital energy. Launch when Earth and Venus are positioned correctly, apply thrust to drop into a transfer orbit, coast for 3 to 4 months, arrive just as Venus reaches the same point in space. It's almost elegant in its simplicity, but that simplicity ends at arrival. Venus itself is a lesson in humility, a reminder that the universe contains places we can touch but never hold, worlds we can measure but never stand upon for more than fleeting moments, our toxic twin. brilliant in the sky, deadly up close. Which brings us gently to the question of the planet we visited most successfully, the one that has captured our imagination perhaps more than any other. Mars has occupied a special place in human imagination for over a century. It's close, visible to the naked eye as a reddish star, and it seems, at least from a distance, potentially habitable. The journey to Mars takes 6 to 9 months, depending on the trajectory and launch window, a span of time that feels almost manageable compared to the years required for the outer planets. This relative accessibility has made Mars the focus of more missions than any other planet except Venus, and the primary target for human exploration beyond Earth. The distance to Mars varies more dramatically than Venus, because Mars has a more elliptical orbit and is farther from the Sun. At closest approach, opposition, Mars can be as near as 33.9 million miles from Earth. At its farthest, conjunction, when the Sun sits between Earth and Mars, the distance swells to about 250 million miles. Launch windows for Mars missions occur roughly every 26 months. When Earth and Mars align favourably, miss the window and you wait more than 2 years for the next one. A typical Mars mission uses a Hohmann transfer orbit, the fuel-efficient elliptical path that was first calculated in the 1920s. The spacecraft launches from Earth, escapes Earth's gravity, and follows an arc that crosses Mars's orbit at the exact moment Mars arrives at that point. The journey takes about 7 to 9 months for most missions. Mariner 4, the first successful Mars flyby in 1965, took 228 days. The Viking landers in the 1970s took about 11 months. More recent rovers like Curiosity and Perseverance made the trip in roughly 7 months. The consistency of these timelines across decades shows we're working with fundamental orbital mechanics. We can't substantially speed up the journey without burning enormous amounts of fuel. Some proposals exist for faster trajectories using more powerful propulsion systems, potentially cutting the travel time to 3 or 4 months, but these remain theoretical. The physics of reaching Mars efficiently settles around 6 to 9 months. And that's what we've accepted. This duration has profound implications for human missions. 6 to 9 months is a long time to live in a spacecraft. Astronauts on the International Space Station serve 6-month tours, so we know humans can survive that long in microgravity, but the ISS is in low Earth orbit, a few hours from home in an emergency. Mars is months away. Any problem, any medical emergency, any technical failure has to be solved with what's on board. There's no quick return, no abort to safety, and then there's the return journey. If you send humans to Mars, you can't bring them home immediately. The orbital mechanics that brought you to Mars won't work in reverse for many months. Earth and Mars have to align again for the return trip. This means a human Mars mission involves staying on the surface for a year to a year and a half, waiting for the planets to reach the right positions, then another 6 to 9 months to get home. Total mission time, 2.5 to 3 years minimum. NASA and other space agencies have studied this extensively. The challenges are not primarily about getting to Mars, which we know how to do. We've landed rovers successfully 8 times. The challenges are keeping humans alive for the round trip, providing enough food and water and air for 3 years, shielding them from radiation, maintaining their physical and mental health in isolation, and ensuring they have the resources to survive on Mars itself during their long stay. But here's what's remarkable. It's all theoretically possible with current or near-future technology. Mars is just barely within reach. The journey is long but survivable. The surface is hostile but manageable with proper equipment. Water ice exists at the poles and underground. The atmosphere, though thin, contains carbon dioxide that could be converted to oxygen and fuel. Mars is hard, genuinely hard, but it's not impossible. It's the next place humans could go if we choose to make the investment and accept the risks. Every 26 months, Earth and Mars align. Every 26 months, there's a window to send something or someone across that gulf. Some windows are better than others because the orbits are elliptical and the distances vary. But the opportunity returns, reliable as clockwork, a cosmic invitation written in orbital mechanics. And we've been accepting that invitation, sending machines, learning what we need to know, preparing slowly for the day when people might follow. The dream of Mars persists not just because it's scientifically interesting, though it absolutely is, but because it's achievable within a human lifetime, within timescales we can actually plan for and execute. 6 to 9 months there, a year on the surface, 6 to 9 months back. It's a journey you could make and return from while your children are still children. That's different from Neptune. That's different from the outer solar system. That's a journey that feels, despite its dangers, somehow possible. And this sense of possibility, this nearness of Mars, leads us to consider what lies beyond, to the giant that dominates the outer solar system. Jupiter sits far beyond Mars, orbiting at an average distance of 484 million miles from the Sun. When Earth and Jupiter are on the same side of the Sun, the distance between them is about 390 million miles. When they're on opposite sides, it stretches to about 600 million miles. This is a different scale entirely from the inner planets, a gulf that takes years to cross even with our fastest spacecraft. The first probe to reach Jupiter was Pioneer 10, launched in 1972. It took 641 days, just over 21 months to make the journey. Pioneer 11 followed, taking a similar amount of time. The Voyager probes, launched in 1977 with more advanced technology and favourable planetary alignments, reached Jupiter in about 18 months. These missions used direct trajectories, relatively straight paths that got them to Jupiter as quickly as possible for flybys. But if you want to orbit Jupiter, to stay and study it rather than just pass by, the journey takes longer. Galileo, launched in 1989, took 6 years to reach Jupiter orbit. It didn't fly directly. It performed gravity assists at Venus and Earth to gain the speed necessary for the journey, following a longer, more complex path. Juno, the most recent orbiter, launched in 2011 and arrived in 2016, a journey of almost exactly 5 years using a gravity assist at Earth. 5 to 6 years. That's the commitment required to place a spacecraft in orbit around Jupiter using current technology and fuel-efficient trajectories. If we wanted to go faster, we could build faster spacecraft, but the fuel requirements increase dramatically. The New Horizons probe, designed to reach Pluto, flew past Jupiter in just 13 months, the fastest transit ever. But it was moving so quickly it couldn't stop. It used Jupiter for a gravity assist to speed even faster toward the outer solar system, stealing momentum from the giant planet. This reveals something fundamental about deep space exploration. The farther you go, the more speed you need, but also the more time you're willing to accept. A flyby mission can move quickly, gathering data during a brief encounter. An orbiter needs to slow down upon arrival to match speeds with its target, and that requires either fuel or time or both. Most missions choose time, using gravitational assists and patient trajectories. Jupiter itself is worth the wait. It's the largest planet in the solar system. Containing more mass than all the other planets combined, its powerful magnetic field creates radiation belts so intense they can damage spacecraft electronics. Its great red spot is a storm larger than Earth that's been raging for centuries. It has at least 95 moons, 4 of which are planet-sized worlds in their own right. Europa might harbour a liquid ocean beneath its icy shell, potentially containing more water than all of Earth's oceans. Ganymede is the largest moon in the solar system, bigger than Mercury. Io is the most volcanically active body we know, its surface constantly reshaped by tidal forces from Jupiter's immense gravity. Studying Jupiter helps us understand planetary formation. It's a gas giant composed mostly of hydrogen and helium, more like a failed star than a rocky planet. It likely formed early in the solar system's history, and its gravity influenced the orbits of everything else. Understanding Jupiter is understanding the architecture of our cosmic neighbourhood, But understanding requires presence, and presence requires patience. 5 to 6 years from Earth to Jupiter orbit. That's longer than many graduate programs. It's time enough for a child to start school and finish elementary. It's a substantial fraction of a human career. And yet, for a mission to Jupiter, it's accepted as normal, expected. We build these spacecraft, launch them, and wait. Mission controllers who are young engineers at launch might be experienced veterans by arrival, and Jupiter is not even particularly far in the scale of the solar system. It's the first of the giant outer planets, the nearest of the truly distant worlds. Beyond it lie Saturn, Uranus, Neptune, each one farther, each one requiring more years, more patience, more commitment to journeys that span significant portions of human life. Which brings us to the ringed world, the jewel of the solar system, a destination that demands the better part of a decade to reach. Saturn orbits the Sun at an average distance of 886 million miles, nearly twice as far as Jupiter. When Earth and Saturn align favourably, the distance between them is about 746 million miles. At their farthest separation, it's over 1 billion miles. This immense distance translates to travel times that measure not in months, but in the better part of a decade. Pioneer 11, after flying past Jupiter, became the first spacecraft to reach Saturn in September of 1979. The total journey from Earth to Saturn took 6 years and 9 months. Though much of that time was spent travelling between Jupiter and Saturn after the Jupiter flyby. Voyager 1 reached Saturn in November 1980, about 3 years after launch, but it had used a gravity assist at Jupiter to speed its journey. Without that assist, the trip would have taken substantially longer. The most comprehensive study of Saturn came from Cassini, one of the most successful planetary missions ever flown. Cassini launched in October of 1997 and arrived at Saturn in July of 2004. 6 years and 9 months of flight time, the spacecraft carried the Huygens probe, built by the European Space Agency, which would later descend to the surface of Titan, Saturn's largest moon. Together, they would spend 13 years exploring the Saturn system, but first they had to get there. Cassini's trajectory was complex and beautiful. It flew past Venus twice, using each encounter to adjust its path and gain speed. Then it returned to Earth for another gravity assist, and finally flew past Jupiter, stealing more momentum from the giant planet. Only after all these carefully planned encounters did it have the velocity and trajectory needed to reach Saturn. The journey was a masterpiece of orbital mechanics, plotted years in advance. Executed with extraordinary precision, 7 years is a long time to wait. Engineers who designed Cassini's instruments were well into different phases of their careers by the time it arrived. Some had retired, some had moved to other projects. But when Cassini fired its main engine to slow down and enter Saturn orbit, when the signal finally reached Earth across the vast distance, the control room erupted in celebration. 7 years of anticipation, 7 years of waiting, fulfilled in a single successful maneuver. Saturn rewarded that patience. The Cassini mission discovered new moons, observed storms the size of Earth, studied the intricate structure of the rings in unprecedented detail, and found evidence of liquid water oceans beneath the icy surfaces of Enceladus and possibly Titan. Enceladus shoots geysers of water ice into space from cracks in its southern pole. Cassini flew through those plumes, tasting the composition, discovering organic molecules and salts that suggest a warm, salty ocean beneath the ice. This small moon, only 300 miles in diameter, might be one of the best places in the solar system to search for life beyond Earth. Titan, larger than Mercury, has a thick nitrogen atmosphere and lakes of liquid methane and ethane on its surface. It rains there, not water, but hydrocarbons, creating a weather cycle entirely alien to Earth. The Huygens probe descended through Titan's atmosphere in January 2005. taking photographs and measurements all the way down, landing on a surface that might have been solid or liquid. Nobody knew for certain. It turned out to be solid with the consistency of wet sand. The images it sent back showed a landscape of rounded rocks and distant hills shrouded in orange haze, a world utterly unlike anywhere else we've seen. All of this discovery required Cassini's presence in orbit around Saturn for over a decade. The journey to get there was just the beginning. And when the mission finally ended in September 2017, when Cassini deliberately dove into Saturn's atmosphere to avoid any possibility of contaminating the potentially habitable moons, it had spent 20 years in space. 7 years travelling, 13 years exploring, 2 decades total from launch to final plunge. There's something Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. There's something profound in that timescale. 20 years is long enough to raise a child to adulthood. It's long enough for someone to complete their education, start a career, build a life. And throughout all that time, this spacecraft was out there, moving through space, sending back images and data, expanding human knowledge one observation at a time. The people who launched it aged. The world changed. Technology advanced. And Cassini kept working, kept transmitting, kept exploring. No future mission to Saturn is currently funded or scheduled, though many are proposed. The next spacecraft to orbit Saturn, if and when it's built, will face the same journey, 6 to 7 years minimum from Earth to arrival. That's the price of distance, the cost measured in time and patience. And perhaps that's fitting for a planet as majestic and complex as Saturn. A world that rewards careful, sustained observation, that reveals its secrets slowly to those willing to wait and watch. Let's allow that image to settle. The thought of a spacecraft travelling for 7 years through darkness and silence to reach the ringed planet, and consider what lies even farther out. Uranus orbits at an average distance of 1.8 billion miles from the Sun, more than twice Saturn's distance. It's so far that it takes 84 Earth years to complete a single orbit around the Sun. The planet wasn't even discovered until 1781, when William Herschel spotted it through a telescope, the first planet ever found that wasn't known to ancient astronomers. For most of human history, we didn't know Uranus existed. Even now it remains mysterious, visited only once by a single spacecraft. That spacecraft was Voyager 2, the only human-made object ever to visit Uranus. Voyager 2 launched in August of 1977, taking advantage of a rare alignment of the outer planets that occurs only once every 176 years. This alignment allowed the spacecraft to visit Jupiter, Saturn, Uranus and Neptune in sequence. Using gravity assists at each planet to speed toward the next. It's called the Grand Tour, and it was a unique opportunity that won't come again until the 22nd century. Voyager 2 reached Uranus in January of 1986, 8.5 years after launch. 8.5 years of flight through the outer solar system far from the Sun, running on nuclear power because solar panels wouldn't work in such dim light. The encounter lasted only a few hours. Voyager 2 flew past at tremendous speed, its cameras capturing images, its instruments measuring magnetic fields and radiation, and then it was gone, speeding onward toward Neptune. Those few hours remain our only close-up look at Uranus. We learned that it's a strange world, tipped on its side so that its rotation axis lies nearly in the plane of its orbit. Every other planet spins more or less upright, but Uranus rolls along like a barrel. One pole faces the Sun for 42 years, experiencing constant daylight, while the other endures 42 years of darkness. Then they switch. The cause of this extreme tilt remains uncertain, though most scientists believe Uranus suffered a massive collision early in its history. Something big enough to knock it sideways. Uranus is an ice giant, composed primarily of water, methane and ammonia ices surrounding a rocky core. Its atmosphere contains methane, which absorbs red light and gives the planet its distinctive blue-green colour. It has faint rings discovered in 1977 and 27 known moons, most of them small and icy. The largest moons, Miranda, Ariel, Umbriel, Titania and Oberon, show varied geology. Miranda in particular is bizarre, with a surface that looks like it was shattered and reassembled, cliffs twice the height of Mount Everest, and terrain that suggests a complex and violent history. But all this knowledge comes from that single flyby in 1986, plus whatever we can see through telescopes from Earth and space. No orbiter has ever circled Uranus. No detailed long-term study has been conducted. For a planet in our own solar system, Uranus remains remarkably unknown. The reason is simple: distance and time. Uranus is so far that reaching it takes the better part of a decade with current technology. Voyager 2 needed 8.5 years with gravitational assists. A direct flight without those assists would take substantially longer, potentially 12 to 15 years depending on the trajectory and launch energy. That's a massive commitment of resources and patience. Several missions to Uranus have been proposed over the years. Scientists want to return, to orbit, to study the tilted world in detail, to understand its atmosphere and magnetic field and strange moons. But the proposals compete with missions to other targets, and the sheer length of the journey makes Uranus a difficult sell. By the time a Uranus orbiter arrives, the scientists who proposed it might be retired. The instruments designed with current technology might be outdated by the time they're used. It's hard to maintain institutional and political support for a mission that won't produce results for 12 to 15 years. And yet, there's value in exploring every world in our solar system. Each planet teaches us something about planetary formation, about the conditions that create different types of worlds, about the range of possibilities that exist in the universe. Uranus, with its sideways spin and ice giant composition, represents a class of planet that might be extremely common around other stars. Understanding Uranus helps us understand exoplanets we're discovering thousands of light years away. The distance to Uranus also reminds us that our solar system is vast beyond easy comprehension. We think of the planets as neighbours, as part of our cosmic neighbourhood, and they are. But the neighbourhood is huge. The gap between Saturn and Uranus is larger than the distance from the Sun to Saturn. Space expands as you move outward. The distance is growing exponentially. The travel times stretching into significant fractions of a human life. And beyond Uranus lies Neptune, even farther, even colder, the last of the major planets, the edge of the realm where giant worlds circle our star. To reach it requires not just years, but over a decade of patient flight through the outer darkness. Neptune orbits at an average distance of 2.8 billion miles from the Sun, nearly 30 times Earth's distance. It takes 165 Earth years to complete a single orbit. Since its discovery in 1846, it has completed only one full trip around the Sun, finishing that first observed orbit in July of 2011. It's a world of blue methane clouds and violent storms, the windiest planet in the solar system, with gusts reaching over 1,000 miles per hour. And it is staggeringly far away. Voyager 2, the only spacecraft ever to visit Neptune, reached it in August of 1989. 12 years after launch, 12 years of flight through space. The spacecraft that left Earth in 1977 arrived at Neptune in a world quite different from the one it departed. The Cold War was ending. The Berlin Wall would fall 3 months later. The technology that seemed cutting edge in the late 70s was obsolete by the late 80s. But Voyager 2 kept working, kept transmitting, kept following the trajectory plotted more than a decade before. The encounter with Neptune lasted only hours, as with Uranus. Voyager 2 flew past at 38,000 miles per hour relative to the planet, far too fast to stop or orbit. It photographed the blue world, discovered 6 new moons, observed the Great Dark Spot, a storm system similar to Jupiter's Great Red Spot, and studied Triton, Neptune's largest moon. Triton turned out to be one of the most interesting worlds in the solar system. It's the only large moon that orbits its planet backward, retrograde, moving opposite to Neptune's rotation. This strongly suggests Triton didn't form with Neptune but was captured, probably a dwarf planet from the Kuiper belt that wandered too close and was gravitationally trapped. Triton is geologically active despite being one of the coldest places in the solar system. Voyager 2 observed nitrogen geysers erupting from its surface, shooting plumes 5 miles high, a captured world active and strange, orbiting the outermost giant planet. And then Voyager 2 was past Neptune, racing out of the solar system, its primary mission complete. It continues to operate today, over 46 years after launch, now in interstellar space beyond the influence of the sun's solar wind. It carries a golden record, a phonograph with sounds and images from Earth, a message in a bottle for any intelligent life that might find it millions of years from now. No other spacecraft has visited Neptune, and none are planned. The distance is too great, the journey too long. The cost too high for the current priorities of space exploration. Reaching Neptune with current technology requires 12 to 15 years minimum, depending on whether gravity assists are available. A direct flight could take even longer. That's a substantial portion of a human career, a significant chunk of a human life. Think about what 12 to 15 years means. A student entering high school when the mission launches would be finishing a graduate degree by arrival. A young professional in their 20s would be approaching middle age. Children born at launch would be teenagers by the time the spacecraft reaches its destination. This is not a timescale we're naturally comfortable with. We're impatient creatures, adapted for short-term thinking, uncomfortable with delayed gratification measured in decades. But the universe doesn't care about our comfort. Neptune orbits where it orbits, distant and indifferent, and if we want to study it up close, we accept the journey time or we don't go at all. So far, we've chosen mostly not to go. Voyager 2's flyby in 1989 remains our only visit, and the images and data from that brief encounter are all we have beyond what telescopes can reveal. There have been proposals for a Neptune orbiter, missions that would study the planet and Triton in detail, perhaps even land on Triton's surface. But these remain proposals, concepts, dreams on paper. The political and financial will to commit to a 12 to 15-year mission hasn't materialised. Other targets, closer and more accessible, draw the limited resources available for planetary exploration. Yet Neptune persists in its distant orbit, a beautiful blue world at the edge of the planetary realm, a reminder of how much of our own solar system remains unexplored. We've sent spacecraft to every major planet now, but most of those visits were brief flybys decades ago. The outer solar system from Jupiter outward remains largely mysterious, known through fleeting glimpses rather than sustained study. And this brings us to a question worth contemplating as we think about these enormous travel times, these decade-long journeys to the outer planets. What determines how fast we can travel through space? We've talked about travel times ranging from months to years to over a decade, and you might wonder why we can't simply build faster spacecraft, engines powerful enough to cut these journeys dramatically. The answer involves physics, engineering, and the fundamental constraints of rocket propulsion as we currently understand it. A spacecraft's speed depends on how much momentum it can generate. And momentum comes from throwing mass in one direction to push the spacecraft in the other. This is Newton's third law. Every action has an equal and opposite reaction. A rocket engine burns fuel, expelling hot gas at high velocity out the back, and the spacecraft moves forward. The faster you expel the exhaust and the more mass you expel, the more speed you gain. But here's the problem. You have to carry all that fuel with you. And fuel has mass. The more fuel you carry, the heavier your spacecraft and the more fuel you need to accelerate that mass. This leads to diminishing returns. To go twice as fast, you don't need twice as much fuel. You need exponentially more fuel, and eventually you reach a point where the spacecraft is mostly fuel with a tiny payload, and it's still not fast enough. Chemical rockets, the kind we use for most launches today, can achieve exhaust velocities of about 2 to 4.5 miles per second depending on the fuel. This limits how much speed they can provide. To reach high velocities, spacecraft use the planet they're launched from as a starting point, inheriting Earth's orbital velocity of 18 miles per second around the Sun, then adding to it with rocket burns. They also use gravity assists, swinging past planets to steal orbital momentum, gaining speed without burning additional fuel. The Voyager spacecraft, for instance, didn't carry enough fuel to reach the outer planets on their own. They used gravity assists at each planet, carefully planned flybys that bent their trajectories and increased their velocities. By the time Voyager 1 passed Saturn, it was moving fast enough to escape the solar system entirely, the first human-made object to reach escape velocity through a combination of its own engines and gravitational boosts. The fastest spacecraft we've ever built. In terms of heliocentric speed relative to the Sun, is the Parker Solar Probe, designed to study the Sun's corona. It uses Venus gravity assist to progressively lower its orbit, falling closer and closer to the Sun, and as it falls it accelerates. At its closest approach to the Sun, Parker reaches speeds over 192,000 meters per second, about 430,000 miles per hour. At that speed, you could travel from New York to Tokyo in under a minute. But even at that incredible velocity, crossing the solar system takes years. Parker is fast relative to the Sun, but the solar system is enormous. If we pointed Parker Solar Probe at Neptune right now at full speed, it would still take years to arrive. Speed helps, but it doesn't eliminate the fundamental constraint of distance. There are theoretical propulsion systems that could do better. Ion engines, which accelerate charged particles using electric fields, can run for months or years continuously, gradually building up enormous velocities. They produce very low thrust, too weak to launch from Earth's surface, but in the vacuum of space they can eventually achieve higher speeds than chemical rockets. NASA's Dawn mission used ion propulsion to visit Vesta and Ceres in the asteroid belt, and the technology works well for long-duration missions where you're willing to accelerate slowly over time. Nuclear propulsion is another possibility. Using nuclear reactors or even nuclear pulse propulsion, detonating small nuclear charges behind the spacecraft to push it forward, could theoretically provide much higher thrust and efficiency than chemical rockets. These concepts were studied seriously in the 1960s and 70s, but political and environmental concerns halted development. Still, the physics works, and if we ever decide to commit to fast missions to the outer solar system, nuclear propulsion is likely how we do it. Then there are more speculative ideas: antimatter propulsion, fusion drives, solar sails pushed by laser beams from Earth, even concepts involving space-time manipulation that verge on science fiction. Some of these might be possible eventually. Some might violate physics we don't yet understand. But none of them exist today, and most won't exist for decades at minimum. What we have now are chemical rockets and ion drives and gravity assists. With these tools, reaching the inner planets takes months, the outer planets take years to over a decade, and anything farther takes even longer. These aren't arbitrary limitations. They're physical realities based on the technology we possess and the laws of motion that govern how objects move through space. And there's a kind of honesty in these constraints. They remind us that space is genuinely vast, that distances are genuinely large, that the universe does not make itself small and convenient for us. We can explore, but only with patience. We can send machines to distant worlds, but the journey will take years. And we have to accept that and plan accordingly. This is part of what makes the achievements of missions like Voyager and Cassini and New Horizons so remarkable. They succeeded not by overcoming the physics, but by working within it, by accepting the years-long journeys and designing spacecraft that could survive them, by choosing patience over speed because patience was possible and sufficient speed was not. Which leads us to consider the psychological and human dimension of these long journeys, the people who dedicate significant portions of their lives to missions that unfold over decades. When Voyager 2 launched in 1977, some of the engineers working on the mission were in their 20s, young professionals at the start of their careers. When Voyager 2 flew past Neptune 12 years later in 1989, those same engineers were in their 40s, experienced veterans, perhaps with children of their own. When Voyager 2 crossed into interstellar space in 2018, 41 years after launch, the youngest members of the original team were approaching retirement, and some had already passed away. The spacecraft outlasted many of the people who built it. It continues to transmit data today, sending back measurements from beyond the heliopause, the boundary where the sun's influence fades, and true interstellar space begins. The signal is faint, taking over 22 hours to reach Earth at the speed of light, and the power from its plutonium generators is gradually declining. Within a few years, Voyager 2 will no longer have enough power to run its instruments. Sometime in the late 2020s or early 2030s, it will fall silent, coasting through space, its mission complete. 50 years from launch to silence. That's longer than many careers, longer than the span from childhood to retirement for some. And this is the reality of deep space exploration. The timescales involved exceed individual human experiences. We launch missions that our children, or even our grandchildren, will see completed. We make commitments that span generations. The Cassini mission to Saturn provides another example. From initial concept in the mid-1980s to end of mission in 2017, Cassini's lifespan was over 30 years. Some scientists proposed instruments for Cassini as graduate students and were senior professors or retired by the time the mission ended. The data collected is so vast that researchers will be analysing it for decades more. Discoveries are still being published from Cassini observations, new insights emerging from old measurements. This creates a strange relationship between the people and the missions. You can dedicate your career to a single spacecraft, to a single distant target, investing years of your life into instruments that will function for a few years, billions of miles away. The reward is knowledge, discovery, the expansion of human understanding. But the cost is time, patience, the acceptance that most of your work happens in waiting, in planning, in analysis of data that arrives after years of anticipation. And there's something beautiful in this patience, in the willingness to think beyond immediate results, to value knowledge that accumulates slowly. It's countercultural in a world that increasingly demands instant gratification, rapid returns, quarterly profits. Space exploration operates on different rhythms, cosmic rhythms, where progress is measured in years and decades, and the payoff is understanding rather than profit. This patience extends to sample return missions, missions that not only visit distant worlds but bring pieces of them back to Earth. NASA's OSIRIS-REx mission, launched in 2016, reached the asteroid Bennu in 2018, collected a sample in 2020, and returned it to Earth in 2023. 7 years from launch to sample return, and that was to an asteroid, a relatively nearby target. Future sample returns from Mars, which NASA and ESA are planning, will take even longer. Launch in the late 20s, arrive at Mars in the early 30s, collect samples, launch them back toward Earth, arrive in the mid to late 2030s, a decade or more from start to finish. These timelines require institutional stability, sustained funding, political will that persists across administrations and elections and changing budgets. They require faith that the work matters enough to continue year after year, even when immediate results are absent. Even when other priorities compete for resources, and they require individuals willing to tie their professional lives to these long arcs of exploration. Mission scientists who know they'll spend 5, 10, 15 years waiting for data. Engineers who design systems that won't be tested in actual mission conditions until years after they're built. Controllers who will guide spacecraft through maneuvers that occur light hours away, where every command takes hours to arrive and confirmation takes hours more to return. There's a kind of devotion in this work, a commitment to something larger than immediate personal benefit. You're contributing to human knowledge, to a collective understanding that will outlast you. The discoveries made by Voyager or Cassini or New Horizons belong to everyone, adding to our species' comprehension of the cosmos. Your name might be on a paper, on a contributor list, but the knowledge itself becomes part of the commons, available to anyone who seeks it. And perhaps this is part of what space exploration teaches us. Patience, long-term thinking, the value of work that spans beyond individual lifetimes. The universe is old, billions of years old. And it will be here billions of years after we're gone. The timescales we find difficult, the years and decades that stretch human patience, are nothing to the cosmos. Neptune doesn't care that it takes 12 years for us to reach it. The stars don't adjust their positions for our convenience. If we want to explore, we accept the universe's terms. We accept the distances, the travel times, the years of waiting. We build our spacecraft, plot our trajectories, launch our missions, and wait. And in that waiting, in that patience, we find a kind of peace, a relinquishing of the need for immediacy, an acceptance of time as it actually unfolds rather than as we wish it would. Let's rest with that thought for a moment. The image of engineers and scientists dedicating decades to missions that will outlive their careers, sending machines to distant worlds and waiting years to see the results, and consider how these long journeys have been achieved not through speed but through cleverness. One of the most elegant solutions to the problem of reaching the outer solar system quickly involves using the planets themselves as accelerators. This technique, called a gravity assist or gravitational slingshot, allows a spacecraft to gain speed without burning fuel, stealing a tiny fraction of a planet's orbital momentum to boost itself to higher velocities. It's a beautiful piece of orbital mechanics, non-intuitive and remarkably effective. Here's how it works. Imagine a spacecraft approaching a planet from behind, moving in the same direction as the planet's orbit but slower. As the spacecraft enters the planet's gravitational field, it begins to fall toward the planet, accelerating just as anything falls when pulled by gravity. The spacecraft swings around the planet in a curved path, passes close by, and then climbs back out of the gravity well on the other side. From the planet's perspective, from a frame of reference moving with the planet, the spacecraft comes in at a certain speed and leaves at the same speed. Energy is conserved. But from the sun's perspective, from the reference frame of the solar system, something remarkable has happened. The spacecraft has gained the component of the planet's orbital velocity in the direction it was already moving. It steals momentum from the planet, speeding up while the planet slows down an infinitesimal amount, far too small to measure given the planet's enormous mass. The result is that the spacecraft can leave the encounter moving significantly faster relative to the sun than when it arrived, without burning any fuel. The planet's gravity did all the work, bending the trajectory and adding velocity. And because planets are massive and move at high orbital speeds, the boost can be substantial. A well-executed gravity assist at Jupiter can add tens of thousands of miles per hour to a spacecraft's velocity. This technique was first proposed theoretically by Michael Minovich in the early 1960s and independently by others around the same time. The first practical use was Mariner 10 in 1973, which used a Venus gravity assist to reach Mercury, but the true masterclass in gravity assists came with the Voyager missions. Voyager 1 and Voyager 2 launched in 1977 to take advantage of a rare alignment of Jupiter, Saturn, Uranus, and Neptune that occurs only once every 176 years. This alignment meant a spacecraft could visit all 4 planets in sequence, using gravity assists at each one to reach the next. Without gravity assists, visiting all 4 planets would require separate missions or impossibly large fuel loads. Voyager 2's trajectory is particularly elegant. It flew past Jupiter in July 1979, using the giant planet's gravity to bend towards Saturn. It reached Saturn in August 1981, used another gravity assist to redirect toward Uranus. It flew past Uranus in January 1986 and used yet another assist to reach Neptune in August 1989. 4 planets in 12 years, each encounter carefully planned years in advance. The trajectory plotted with extraordinary precision. The navigation required for these maneuvers is astonishing. You have to predict where the planet will be months or years in advance. Plot a path that brings the spacecraft to that exact point in space at the exact moment the planet arrives, and aim for a specific altitude above the planet's surface to achieve the desired change in velocity and direction. Miss by a little, and you might not get the boost you need, or you might get too much boost in the wrong direction, sending the spacecraft off course. And you're doing all this from Earth, sending commands that take minutes to hours to reach the spacecraft, receiving confirmation long after the commands execute. By the time you see the result of an engine burn, it's already happened, and if something went wrong, you're correcting it in hindsight. It's like playing pool on a table the size of the solar system, where it takes hours to see if your shot succeeded. The Cassini mission used multiple gravity assists in a more complex way. It flew past Venus twice to gain speed and adjust its trajectory, then returned to Earth for another boost, then flew past Jupiter before finally reaching Saturn. Each encounter was precisely calculated to set up the next, a chain of gravitational dominoes falling exactly as planned over 6 years. New Horizons, the mission to Pluto, used a single gravity assist at Jupiter to gain 4,000 miles per hour and save 3 years of travel time. Without that boost, it would have taken 13 years to reach Pluto instead of 9.5. The Jupiter flyby also served as a test of the spacecraft's instruments and a scientific opportunity to study Jupiter's moons and magnetosphere. There are limits to what gravity assists can do. You can only use them when planets are positioned favourably, and those alignments happen on fixed schedules determined by orbital periods. You can only gain so much speed from each encounter, limited by the planet's mass and orbital velocity, and you have to be willing to follow complex indirect paths rather than straight lines. But within those limits, gravity assists are extraordinarily powerful. They've enabled missions that would otherwise be impossible with chemical rockets and realistic fuel budgets. They've allowed us to explore the outer solar system not by overcoming the vast distances, but by borrowing speed from the worlds along the way, each planet giving a little push toward the next. There's something almost philosophical in this approach. We reach distant places not through brute force, but through cooperation with the environment, using what's already there, working with gravity rather than against it. The planets become partners in exploration. Their immense masses and swift orbits gifting us the velocity we need to travel farther, faster than we could alone. And this brings us to contemplate the future possibilities, the missions we might undertake if we continue refining these techniques and combine them with more advanced propulsion. The travel times we've discussed so far assume current technology, chemical rockets, ion drives, and gravity assists. But researchers and engineers are exploring more advanced propulsion systems that could potentially cut journey times, making the outer solar system more accessible and even interstellar space conceivable within human lifetimes. These technologies range from near-term possibilities to speculative concepts that may or may not prove feasible. Nuclear thermal propulsion is one of the most developed advanced concepts. Instead of burning chemical fuel, A nuclear reactor heats hydrogen to extremely high temperatures and expels it through a nozzle. This provides roughly twice the specific impulse of the best chemical rockets, meaning you get twice as much thrust per unit of fuel. NASA and the Department of Energy have tested nuclear thermal engines in the past, most notably during the NERVA program in the 1960s and early 70s. The technology works. Modern designs could be safer and more efficient. A nuclear thermal rocket could potentially cut Mars travel time from 6 to 9 months down to 3 to 4 months, a significant reduction that would decrease astronaut exposure to radiation and microgravity. For outer planet missions, the time savings would be even more dramatic. A nuclear-powered mission to Saturn might take 3 to 4 years instead of 6 to 7. To Neptune, perhaps 6 to 8 years instead of 12 to 15. These are meaningful improvements, but they're not revolutionary. We're still talking about years-long journeys to the outer planets. Nuclear thermal propulsion doesn't change the fundamental physics of orbital mechanics or the vast distances involved. It's better, notably better, but the solar system remains enormous. Nuclear electric propulsion takes a different approach. A nuclear reactor generates electricity, which powers ion or plasma thrusters that accelerate propellant to very high exhaust velocities. The thrust is low, but it can operate continuously for months or years, gradually building up enormous velocities. NASA has studied nuclear electric propulsion for cargo missions to Mars and beyond, where you're not worried about speed for human safety, but want efficient transport of supplies and equipment. Fusion propulsion, if we can ever make it work, would be even better. Fusing hydrogen into helium releases far more energy than fission, and a fusion rocket could theoretically achieve much higher exhaust velocities and thrust than any current system. But we haven't yet built a fusion reactor that produces more energy than it consumes, much less a compact one suitable for a spacecraft. Fusion propulsion remains theoretical, a goal for the second half of this century at earliest. Solar sails represent a completely different approach. No fuel at all, just large reflective sails pushed by sunlight or by laser beams from Earth or from satellites. Light carries momentum, and reflecting photons imparts a tiny force on the sail. The force is minuscule, but it operates continuously, never running out of fuel because the sun keeps shining or the lasers keep firing. Over time, a solar sail can build up considerable speed. The Japanese spacecraft Icaros demonstrated solar sail technology in 2010, successfully using sunlight to navigate through interplanetary space. The Planetary Society's LightSail 2, launched in 2019, raised its orbit using only solar radiation pressure. These are small probes, but they prove the concept works. For interstellar missions, laser-push solar sails could theoretically reach a significant fraction of light speed. The Breakthrough Starshot initiative proposes using powerful Earth-based lasers to accelerate tiny sail-equipped probes to 20% of light speed, fast enough to reach the nearest stars in 20 to 30 years. At that velocity, you could reach Neptune in hours, but the engineering challenges are enormous. The sails must be incredibly thin and light, the lasers must be impossibly powerful and precisely aimed, and there's no way to slow down at the destination. You flash past at a fifth of light speed, gathering data for a few seconds, and then you're gone into the void. Antimatter propulsion is theoretically the most powerful rocket possible. When matter and antimatter meet, they annihilate, converting their entire mass into energy with 100% efficiency according to Einstein's famous equation E equals mc squared. A tiny amount of antimatter could provide enormous thrust. The problem is we can currently produce only microscopic amounts of antimatter at tremendous cost, and storing it without letting it touch normal matter and annihilate prematurely is extraordinarily difficult. If we could ever produce and store antimatter in useful quantities, an antimatter rocket could reach Mars in weeks, the outer planets in months, and Alpha Centauri in decades. But this technology is so far beyond our current capabilities that it's hard to even estimate when or if it might become practical. And then there are even more speculative ideas that verge on or cross into science fiction. Warp drives that manipulate space-time, wormholes that create shortcuts through space, reactionless drives that somehow produce thrust without expelling mass. Most physicists believe these violate known physics or require exotic materials and conditions that may not exist. They're fun to think about, but they're not technologies we can develop with foreseeable engineering. What we're left with, for the next several decades at least, are incremental improvements on existing methods. Chemical rockets will get more efficient. Ion drives will become more powerful. Nuclear propulsion might finally be developed and deployed. Gravity assists will be planned with increasing precision, and journey times will decrease, but not drastically. Mars might become a 3 to 4 month trip instead of 6 to 9. Saturn might be reachable in 3 to 4 years instead of 7. Neptune in 6 to 8 years instead of 12 to 15. These improvements matter. Shorter trip times mean less radiation exposure for astronauts, lower mission costs, faster return of scientific data. But they don't fundamentally change the paradigm. The outer solar system will still require years of patience. Interstellar space will still be beyond our reach in practical terms. And maybe that's okay. Maybe accepting the limitations, working within them creatively and patiently, is part of the wisdom of exploration. We're not entitled to easy access to the cosmos. We have to earn every mile, every discovery, every image of a distant world. And perhaps the effort, the years of planning and waiting and hoping, makes the achievement more meaningful when it finally arrives. Which brings us to think about what all these travel times mean for human exploration specifically, for the dream of sending people, not just robots, to the planets. All the journey times we've discussed take on new dimensions when you consider sending humans instead of robots. A spacecraft can wait 12 years to reach Neptune. It doesn't get bored or lonely. It doesn't need food or water or psychological stimulation. It doesn't suffer bone loss from microgravity or radiation damage to its cells. Humans, fragile and complex and alive, face challenges that robots simply don't encounter. The longest any human has spent in space continuously is 437 days, achieved by Russian cosmonaut Valery Polyakov aboard the Mir space station in 1994 to 1995. Astronaut Scott Kelly spent 340 days aboard the International Space Station in 2015 to 2016. We know from these long-duration missions that humans can survive in microgravity for over a year, but not without cost. Bones lose density in microgravity, about 1 to 2% per month, concentrated in the weight-bearing bones of the legs and hips. Muscles atrophy without the constant resistance of gravity. The cardiovascular system decalibrates, the heart becoming weaker because it doesn't have to pump blood upward against gravity. Vision can change due to fluid pressure shifts in the skull. The immune system weakens. Radiation exposure accumulates, increasing cancer risk. Astronauts on the ISS mitigate these effects through vigorous daily exercise, 2 to 3 hours every day on treadmills and resistance machines, maintaining bone and muscle as much as possible, but they're still in low Earth orbit, still partially protected by Earth's magnetic field, still only a few hours from home if a medical emergency arises. A mission to Mars or beyond is fundamentally different. The trip to Mars takes 6 to 9 months each way, plus a stay on the surface of a year to a year and a half waiting for the return launch window. Total mission time, 2.5 to 3 years minimum. During the outbound and return flights, astronauts would be in microgravity, exercising constantly to maintain fitness, exposed to cosmic radiation far beyond what ISS astronauts experience. There's no aborting to Earth if something goes wrong. No resupply missions. Everything they need must be carried with them or produced on Mars. Psychologically, the isolation would be extreme. Communication with Earth has a time delay, anywhere from 3 to 22 minutes one way depending on the relative positions of Earth and Mars. You can't have a conversation. You can send messages and wait for replies, Like emails across the void, the crew would be on their own, making decisions in real time, dealing with emergencies without mission control's immediate guidance. The spacecraft would need to be larger than anything we've built for human spaceflight so far, with room for exercise, privacy, meaningful work, psychological health. 6 to 9 people living in close quarters for years, unable to go outside, unable to return home, dependent on life support systems that cannot fail. The social and psychological dynamics would be challenging in ways we can only partially predict from analogue studies on Earth. And that's just for Mars, the closest and most accessible planet beyond Earth. Missions to the outer solar system would be far worse. A mission to Jupiter would take 5 to 6 years round-trip minimum. Saturn, 12 to 14 years. These durations approach or exceed the time required to raise a child from birth to adolescence. No human has ever been away from Earth for that long. We don't fully know what a decade or more in space would do to the human body and mind. The radiation exposure alone might be prohibitive. Beyond Earth's protective magnetic field, cosmic rays and solar particle events deliver doses that increase cancer risk significantly. A 3-year Mars mission might increase an astronaut's lifetime cancer risk by several percentage points, generally considered acceptable for a voluntary mission. A 10-year Saturn mission would multiply that risk proportionally. We would need better shielding, perhaps water walls or hydrogen-rich materials surrounding the habitat, adding mass and complexity. Food is another challenge. You can't carry 3 years of food for a crew. It's too heavy. You'd need to grow at least some of it, recycling waste into nutrients, creating a closed-loop life support system. NASA and others have studied space agriculture extensively, but it's never been done on the scale required for multi-year deep space missions. Then there's the question of purpose. Why send humans to Jupiter or Saturn when robots can do the science more cheaply and safely? Robots don't need food or air or protection from radiation. They can be sent one way. They're expendable. Humans are not. The answer involves what humans uniquely bring: flexibility, intuition, the ability to make complex decisions and adapt to unexpected situations, to notice things that weren't in the mission plan. Humans can also inspire in ways robots cannot. The Apollo missions to the Moon mattered not just for the science, but for the achievement itself, for the demonstration that humans could leave Earth and walk on another world. The images of Earthrise, of boot prints in lunar dust, of astronauts bounding across the Moon's surface stirred something in the collective human consciousness that no robotic mission could match. But inspiration has to be weighed against risk and cost. A human mission to Saturn would be phenomenally expensive and dangerous, and the scientific return compared to a well-designed robotic mission might not justify the investment. It's a calculation each generation makes for itself. What are we willing to risk? What are we willing to spend for the goal of human presence in deep space? For now, the consensus is focused on Mars. It's far enough to be challenging, close enough to be achievable, potentially habitable enough to be meaningful. Mars is where we're likely to send the first humans beyond the Moon, probably sometime in the 2030s or 2040s if current plans hold. And that 3-year round-trip mission will teach us an enormous amount about long-duration spaceflight, about keeping humans alive and healthy in deep space, about what's required for even farther journeys. Perhaps one day, if we solve the propulsion and life support and radiation challenges, if we develop technologies we don't yet possess, humans might venture to Jupiter's moons or Saturn's Titan. But that's not soon. That's for future generations, for people not yet born who will inherit the knowledge we're gathering now and build on it. For the present, the outer solar system belongs to our robotic ambassadors, patient and tireless, and that seems right. We learn first through exploration with machines, understand the environments, develop the technologies, and only then, if ever, follow with human presence. Let that thought rest as we turn to something simpler and more direct. What does all this distance mean in terms of light, in the time it takes for signals and images to cross the void? Everything we've discussed so far involves objects with mass travelling through space at speeds far slower than light. But there's another kind of journey to consider, the journey of information, of radio signals and images and commands travelling at the speed of light from spacecraft to Earth and back again. And even at light speed, the fastest speed possible in the universe, communication across the solar system takes time, sometimes hours, introducing delays that fundamentally shape how we explore distant worlds. Light travels at 186,000 miles per second in a vacuum. That's fast enough to circle Earth's equator 7.5 times in 1 second. But space is vast, and even light takes measurable time to cross planetary distances. The Moon is about 239,000 miles from Earth. Light takes 1.3 seconds to travel that distance. When astronauts on the Moon spoke to Mission Control, there was a noticeable delay, a few seconds round trip for a signal to reach Earth and a response to return. It's manageable, a bit awkward, but manageable. Mars at its closest is 33 million miles away. Light takes about 3 minutes to cross that gap. At its farthest 250 million miles, light takes 22 minutes. For most Mars missions, when Mars is somewhere between these extremes, the communication delay is 10 to 15 minutes each way. You send a command, quote 1, 20 minutes later. You receive confirmation that the command was executed. This delay makes real-time control impossible. You can't drive a Mars rover with a joystick like a remote-controlled car. The lag is too great. Instead, the rover has to be semi-autonomous. Controllers on Earth plan a day's worth of activities, upload the commands overnight, and the rover executes them the next Martian day while controllers sleep. The next day, they receive the data and images from yesterday's activities, verify everything worked as expected, plan the next day's tasks, and the cycle repeats. Every Mars mission operates this way. The delay forces patience, forces careful planning, forces trust in the autonomy of the robots we send, and it works, but it's slow. A rover might travel only a few dozen meters a day, not because it's incapable of moving faster, but because controllers need time to analyze the terrain, plan the path, and wait for communication. For the outer planets, the delays are even more extreme. Jupiter, at its average distance of about 484 million miles, is about 43 light minutes away. That's 43 minutes for a signal from a spacecraft to reach Earth, and another 43 minutes for a response to return. Round-trip communication time, 86 minutes, nearly an hour and a half. When the Juno spacecraft performs a close flyby of Jupiter, passing within a few thousand miles of the cloud tops, the encounter happens in virtual silence from Earth's perspective. The spacecraft is programmed in advance, executing its observations autonomously. By the time controllers on Earth see the data streaming in, the flyby is long over. Juno has already completed its maneuvers, taken its measurements, and moved on. Controllers can only watch and hope everything went as planned. Saturn is about 80 light minutes away on average. Voyager 2's signals from Uranus took 2 hours and 45 minutes to reach Earth. From Neptune, over 4 hours. When Voyager 2 flew past Neptune in 1989, controllers sent the commands for the encounter sequence hours in advance, then waited. The spacecraft executed the flyby, passing within 3,000 miles of Neptune's cloud tops, photographing Triton, measuring magnetic fields, all on its own. Hours later, the data began arriving, proof that the encounter had succeeded, a message from the edge of the planetary realm telling us what it had found. Voyager 1 is now about 15 billion miles from Earth. Over 22 light hours away, a signal from Voyager 1 takes nearly a full day to make the round trip to Earth and back. We can still communicate with it, still send commands and receive data, but the process is slow, measured in days for confirmation. This expansion of communication time mirrors the expansion of travel time. The farther you go, the longer everything takes. The journey itself, the messages home, the wait for instructions. distance in space imposes delays on every level, slowing exploration to rhythms dictated by physics, and there's no way around it. Light speed is the absolute limit. Nothing can travel faster. Einstein's special relativity is unambiguous on this point. Mass cannot reach light speed, and information cannot exceed it. No matter what technology we develop, we will always be subject to these delays when working at planetary and interplanetary distances. The Voyager spacecraft are approaching the limits of what we can communicate with using current technology. Their transmitters, powered by decaying plutonium, are weak. Their signals, spread over billions of miles, are incredibly faint by the time they reach Earth. We receive them with enormous radio antennas, part of NASA's Deep Space Network, arrays of 70-metre dishes in California, Spain, and Australia that can detect signals as weak as a few quadrillionths of a watt. It's astonishing that we can hear them at all. Eventually, Voyager's power will fade, the transmitters will fall silent and will lose contact. The spacecraft will continue onward, coasting through interstellar space, carrying their golden records, messages to any intelligence that might find them millions of years hence. But for us, they'll be gone, invisible and mute, lost in the immensity. Other spacecraft will follow eventually. New Horizons is also on an escape trajectory, leaving the solar system after its flyby of Pluto and Archon, heading outward into the Kuiper belt and beyond. It will fall silent in the 2030s when its power runs out, but it too will keep travelling, an emissary from humanity drifting into the cosmic dark. These missions remind us that exploration is not just about reaching destinations, but about maintaining connection, about the fragile thread of radio signals linking us to our distant machines, the precious data flowing back across the void. And the farther we send them, the more tenuous that thread becomes, stretched across light hours and eventually light days, until finally it snaps, and we're left with silence. But even in silence, even when the signals cease, the spacecraft persist. They carry our designs, our intentions, our curiosity out into the universe. And in that persistence there's a kind of immortality, a reaching beyond ourselves that continues long after we've lost the ability to observe it, which leads us to contemplate the most distant destinations, the places beyond the planets where our spacecraft have ventured and where light itself takes days to travel. The planets, even distant Neptune, are not the edge of the solar system. Beyond Neptune lies the Kuiper belt, a vast region of icy bodies, remnants from the solar system's formation. Stretching from Neptune's orbit at about 2.8 billion miles from the Sun out to roughly 4.6 billion miles. And beyond even that lies the scattered disk, the heliopause where the solar wind fades, and eventually the Oort cloud, a theoretical sphere of comets extending halfway to the nearest stars. New Horizons, launched in January 2006, became the first spacecraft to visit the Kuiper belt. It flew past Pluto in July 2015. 9.5 years after launch, travelling farther from Earth than any previous mission designed to study a specific target. Pluto orbits at an average distance of 3.7 billion miles from the Sun, about 40 times Earth's distance. Light from the Sun takes over 5 hours to reach Pluto. A radio signal from New Horizons took 4.5 hours to reach Earth during the Pluto encounter. The journey to Pluto was extraordinarily fast by deep space standards. New Horizons is one of the fastest spacecraft ever launched, leaving Earth at over 36,000 miles per hour, so fast it crossed the Moon's orbit in just 9 hours. It used a gravity assist at Jupiter to gain even more speed, reaching over 52,000 miles per hour relative to the Sun, and then coasted for 9 years across the outer solar system. Even at that velocity, the trip took nearly a decade, 9.5 years from launch to Pluto. The principal investigator, Alan Stern, proposed the mission concept in the early 1990s. By the time New Horizons arrived at Pluto, more than 2 decades had passed from initial concept to flyby. Students who were in elementary school when the mission was first proposed were finishing graduate school by the time it reached its destination. Pluto itself proved to be far more complex and beautiful than anyone anticipated. A world with a nitrogen atmosphere, mountains made of water ice as hard as rock in the extreme cold, vast plains of frozen nitrogen, possible cryovolcanoes, and a heart-shaped region named Tombor Regio after Pluto's discoverer. The images sent back, taking hours to transmit at the slow data rates possible across such distance, revealed a world that was geologically active despite being billions of miles from the Sun, despite receiving only a tiny fraction of the sunlight Earth enjoys. After Pluto, New Horizons continued outward. In January 2019, it flew past a small Kuiper belt object officially named 486958 Arakoth, informally nicknamed Arakoth, a contact binary about 21 miles long shaped like a snowman. This encounter took place 4 billion miles from the Sun, even farther than Pluto, and required extraordinary navigation. The object was discovered only in 2014 using the Hubble Space Telescope, specifically to provide a post-Pluto target for New Horizons. The team had to locate a suitable object in the spacecraft's path, then aim for something 20 miles across from billions of miles away and hit it. The flyby succeeded. New Horizons passed within 2,300 miles of Arakoth, capturing detailed images of this pristine relic from the solar system's birth. Arakoth is a contact binary. 90 minutes. You've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. Arakoth is a contact binary, 2 lobes that formed separately and gently merged, never having suffered a violent collision, never having been substantially altered since formation 4.5 billion years ago. It's a glimpse into the past, into the conditions that existed when the planets were forming, frozen in time by the extreme cold and distance from the Sun. New Horizons is now over 5 billion miles from Earth and continues to move outward at about 32,000 miles per hour, slowing slightly due to the Sun's gravity, but not enough to prevent eventual escape from the solar system. Its power will last until the mid-2030s, and scientists hope to find another Kuiper belt object to study if one can be located in the spacecraft's path. But even if no more targets are found, New Horizons will keep transmitting data about the interplanetary environment, the particles and magnetic fields in the outer solar system, until its plutonium generators finally fail. Beyond the Kuiper belt, at roughly 9 to 10 billion miles from the Sun, the Voyager spacecraft crossed the heliopause, the boundary where the solar wind pressure balances against the pressure of the interstellar medium. Voyager 1 crossed in August 2012, at a distance of about 11.7 billion miles. Voyager 2 crossed in November 2018 at a slightly closer distance. They are now in interstellar space, the first human-made objects to leave the Sun's protective bubble of charged particles and enter the realm between stars. The data they send back is unique and irreplaceable. They measure the density and composition of interstellar plasma, the magnetic fields that pervade the galaxy, cosmic rays that fill the space between stars. No other spacecraft have ventured this far with working instruments. And they're still transmitting, still sending back measurements, over 46 years after launch, a testament to the engineering and longevity of 1970s technology. But they are slowing down in terms of data return. Power levels drop about 4 watts per year as the plutonium decays. NASA has been shutting down instruments one by one to conserve power, prioritizing those measuring the interstellar environment. By the late 2020s, both Voyagers will likely fall silent, unable to power their transmitters, and will lose contact. They won't stop moving though. Voyager 1 is heading roughly toward the constellation Ophiuchus. In about 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445. Voyager 2 is heading toward the constellations of Sagittarius and Pavo. In roughly 40,000 years, it will pass near a star called Ross 248. Neither will come particularly close to any star for hundreds of thousands or millions of years. They're adrift in the vast emptiness between stars, and they will be for longer than human civilization has existed. And this brings us to the humbling reality of interstellar distances. The nearest star system, Alpha Centauri, is about 4.4 light-years away, roughly 25 trillion miles. At Voyager 1's current speed of about 38,000 miles per hour, it would take over 70,000 years to reach Alpha Centauri if it were headed in that direction, which it isn't. The fastest spacecraft we've built, the Parker Solar Probe at its peak velocity, could theoretically reach Alpha Centauri in about 6,000 years. That's still longer than recorded human history. Even if we could build a spacecraft travelling at 10% of light speed, a velocity far beyond our current capabilities, the trip would take 44 years one way. Launch a mission, and you might be retired or deceased before it arrives. Send a signal when it gets there, and another 4.4 years pass before we receive confirmation. The solar system, vast as it is a tiny island in an ocean of emptiness. The distances between stars dwarf the distances between planets, in the same way that the distances between planets dwarf the distances we travel on Earth. And yet, our spacecraft have reached the edge of our island, have crossed into the interstellar ocean, are drifting outward into that immensity. It's both an achievement and a reminder of our smallness. We've reached the boundary of the sun's influence, but the nearest stars remain impossibly far, separated by gulfs of space and time that may always be beyond our reach, at least with anything resembling current technology. Let's rest with that thought for a moment. The image of Voyager 1 and 2, and New Horizons and eventually other craft, sailing outward into the dark, growing fainter and more distant, carrying fragments of human curiosity into the cosmos, while we remain behind, watching from our pale blue dot, contemplating the distances they cross and the time it takes to cross them. We've travelled together through the solar system, calculating journey times, understanding orbital mechanics, contemplating the years required to reach distant worlds. But perhaps there's something deeper to consider beyond the numbers and the physics, something these distances teach us about our place in the universe and the nature of exploration itself. Distance in space is not just a measure of miles. It's a measure of patience, of commitment, of the willingness to undertake endeavours whose completion extends beyond immediate gratification. When we launch a mission to Saturn that takes 7 years to arrive, we're making a statement about what we value: knowledge for its own sake, understanding that accumulates slowly, achievements that benefit future generations more than our own. This is countercultural in a world increasingly oriented toward instant results, toward quarterly earnings and viral content and rapid returns on investment. Space exploration operates on timescales that seem almost anachronistic, reminders of an earlier era when people planted trees they'd never see mature, built cathedrals that took generations to complete, invested in futures they wouldn't personally experience. And there's a kind of wisdom in that perspective, a recognition that not everything valuable can be rushed, that some things are worth waiting for, worth working toward, even if you won't see the final result. The scientists who proposed Cassini in the 1980s knew they'd be well into their careers by the time it reached Saturn. Some knew they might not live to see the mission's end. But they proposed it anyway, designed it, fought for its funding, built it, and launched it. The knowledge it would gather justified the wait. Distance also teaches humility. We like to think of ourselves as masters of our environment, capable of bending nature to our will through technology and ingenuity. But the solar system doesn't bend. The planets orbit where they orbit, moving at speeds dictated by gravity and momentum, indifferent to our convenience. We can send spacecraft to visit them, but only by accepting the universe's terms, by working within the constraints of orbital mechanics and the speed of light, by being patient when we'd prefer to be hasty, and perhaps most importantly, distance teaches us perspective. When you contemplate that light from Neptune takes over 4 hours to reach Earth, that Voyager 1 signal takes over 22 hours to arrive, that the nearest star is 4.4 years away at light speed, you begin to grasp the enormity of the cosmos. Earth is a tiny world orbiting an ordinary star in an ordinary galaxy among hundreds of billions of galaxies. The distances between planets are immense by human standards, but trivial on cosmic scales. The distances between stars are far greater, the distances between galaxies greater still. We occupy a vanishingly small fraction of space and time. Our entire civilization, all of human history, has occurred in the blink of an eye compared to the age of the universe. The distances we find so daunting, the years we find so challenging to accept, are nothing to the light years that separate stars, the millions of years that mark cosmic events, the billions of years the universe has existed and will continue to exist. This perspective can be sobering, even humbling, but it can also be strangely comforting. Our problems, however pressing they seem, are temporary and local. The universe continues, vast and patient and indifferent to our anxieties. There's a peace in accepting our smallness, in recognizing that we're part of something much larger than ourselves, something that will persist long after we're gone. And yet, small as we are, we're capable of understanding. We can calculate trajectories, build spacecraft, send them billions of miles through space to rendezvous with distant worlds. We can measure the universe, understand its laws, predict the movements of planets and stars. Our minds, products of this tiny world, can comprehend the cosmos. That's remarkable. That's worth celebrating, even in the face of our limitations and the vast distances we struggle to cross. Which brings us to think about what we've learned from all these distant journeys, the knowledge gained from missions that took years to reach their targets. Every long journey to a distant planet has expanded human knowledge in ways that couldn't have been achieved from Earth. Telescopes, however powerful, can only tell us so much. To truly understand another world, we need to visit it, to measure its environment directly, to see it up close. And the insights gained from these missions have fundamentally changed our understanding of the solar system and planetary science. Consider what we've learned about Mars. Early telescopic observations suggested canals, possibly artificial, signs of intelligent life. The first spacecraft to successfully fly past Mars, Mariner 4 in 1965, revealed a cratered, boon-like surface, disappointing those who hoped for a vibrant, inhabited world. Later orbiters and landers showed a more complex planet. Ancient river valleys suggesting Mars once had liquid water on its surface. Polar ice caps of frozen water and carbon dioxide. Enormous volcanoes including Olympus Mons, the largest in the solar system. A canyon system stretching over 2,000 miles. The Viking landers in 1976 searched for life and found none, or at least nothing conclusive. But they did find a world that was habitable in the past, a world that underwent dramatic climate change, that lost most of its atmosphere, that transformed from a wetter, warmer planet to the cold desert we see today. Understanding how and why this happened helps us understand planetary climate in general, the factors that maintain habitability, the risks that could affect Earth. More recent rovers have confirmed that ancient Mars had lakes and rivers, that liquid water persisted for extended periods, that the chemistry was suitable for life as we understand it. Whether life actually arose on Mars remains unknown, but the possibility is real enough that NASA's Perseverance rover is currently collecting samples, that future missions will return to Earth for detailed analysis. The answers we seek about Mars's past, about whether life existed there, require presence on the surface, require machines that can examine rocks and drill into soil and cache samples for return. This takes time, years of transit and years of surface operations, but it's the only way to know. Uranus and Neptune remain less well understood because we've only visited them once, briefly, but even those quick flybys revealed unexpected findings. Uranus's magnetic field is tilted 59 degrees from its rotation axis and offset from the planet's centre, suggesting a complex interior structure. Neptune, despite receiving very little energy from the distant sun, has the fastest winds in the solar system and active weather. Powered by internal heat left over from its formation, each of these discoveries required the long journeys we've discussed. You cannot discover Europa's ocean from Earth. You cannot land on Titan from Earth. You cannot study Neptune's winds without sending a spacecraft to Neptune. And each discovery raises new questions, suggesting targets for future missions, building on what we've learned to ask better questions, to design better instruments, to seek deeper understanding. The knowledge gained isn't just scientific. It's philosophical. Every world we visit reinforces both the uniqueness of Earth and the ubiquity of planetary processes. Earth is special, the only place we know with abundant surface water, breathable atmosphere and life. But it's also typical, a planet shaped by the same forces that shaped Mars and Venus and the moons of Jupiter, subject to the same gravitational and thermodynamic laws. This dual perspective, Earth as both special and ordinary, informs how we think about our place in the universe. We're not the centre of creation, not uniquely positioned or inherently significant. We're one world among many, one planet orbiting one star in a galaxy of hundreds of billions of stars. And yet Earth is the only place we know where the universe has become conscious of itself, where matter has organised into life and intelligence and culture and curiosity. That's significant even if it's not unique, even if life and intelligence exist elsewhere. The long journeys to distant worlds are investments in understanding, in knowledge for its own sake, in the expansion of human comprehension. Each mission returns data that scientists will study for decades, answering questions and raising new ones, contributing to a body of knowledge that grows generation by generation. And that knowledge belongs to all of us, to humanity collectively, not to any nation or organisation, but to the species, to the inheritors of the curiosity that drives us to explore, which leads us to think about the future, about what missions are planned and what we might learn from the journeys yet to come. The future of planetary exploration is being planned now, in mission concepts and proposals, in budgets and timelines, in the decisions about what we'll send to which worlds over the coming decades. Several missions are already approved and in development, representing commitments to journeys that will span years and decades, continuing the tradition of patient exploration across vast distances. Europa Kuiper, scheduled to launch in October 2024. We'll travel to Jupiter to study Europa's subsurface ocean in detail. The journey will take about 5.5 years using a gravity assist at Mars, arriving at Jupiter in 2030. The spacecraft won't orbit Europa directly because the radiation environment is too harsh for long-term survival. Instead, it will orbit Jupiter and make dozens of close flybys of Europa, mapping the ice shell, measuring its thickness, searching for plumes of water vapour erupting from the surface, analysing the chemistry of the ocean. Europa Kuiper represents our best chance to determine whether Europa's ocean is truly habitable, whether it has the chemical ingredients and energy sources necessary for life. If it does, future missions might attempt to land, to drill through the ice, to explore the ocean directly. But that's decades away at minimum. For now, we orbit and observe, gathering the data needed to design those future missions. Dragonfly, approved for launch in 2028, will send a rotorcraft to Titan, Saturn's largest moon. Yes, a rotorcraft, a drone with 8 rotors that can fly through Titan's thick atmosphere. The journey to Saturn will take about 7 years, arriving in the mid-2030s. Once there, Dragonfly will hop from place to place across Titan's surface, studying the organic chemistry, the methane lakes, the potential for prebiotic chemistry similar to what might have occurred on early Earth. Titan is one of the most intriguing places in the solar system for astrobiology, a world where complex organic molecules form naturally in the atmosphere and rain down on the surface, where liquid exists on the surface and subsurface, where chemistry we don't fully understand creates the orange haze that shrouds the moon. Dragonfly will be the first mission to explore Titan's surface in a mobile way, flying over dunes and lake shores and impact craters, collecting samples and analysing them with onboard instruments. NASA and ESA are also planning the Mars Sample Return mission, one of the most complex missions ever attempted. Perseverance rover on Mars has been collecting samples of rock and soil, caching them in sealed tubes. A future mission will land on Mars, collect these tubes, launch them into Mars orbit, rendezvous with an orbiter that will capture them, and return them to Earth. The entire architecture involves multiple launches, multiple spacecraft, and a decade or more of operations. But the payoff is, and beyond these approved missions are dreams and proposals, sample returns from Enceladus, orbiters for Uranus and Neptune, landers for Europa and Titan, missions to study Pluto's atmosphere more thoroughly, perhaps a probe to enter Jupiter's atmosphere and study its interior. Some of these will happen eventually. Others will remain unfunded concepts, ideas that never quite make it through the competitive process for resources and approval. But the dreaming itself is valuable. It keeps us thinking about where we could go, what we could learn, how we might overcome the challenges of distance and time. Each proposal teaches us something about what's possible, about the trade-offs between cost and capability, about what questions matter enough to justify the investment. Let's hold these future missions in our thoughts, these journeys not yet begun but already planned, and consider how they fit into the larger arc of human exploration. Human exploration has always been characterized by pushing boundaries, by venturing beyond the known into the unknown, accepting risks and uncertainties for the sake of discovery and understanding. The history of exploration on Earth, maritime and terrestrial, provides context for what we were attempting in space, revealing patterns and motivations that persist across different domains and eras. Early human exploration was driven by necessity and curiosity in roughly equal measure. People migrated across continents following game, seeking better climate, expanding into new territories. The Polynesian navigators crossed the Pacific in outrigger canoes, island hopping across thousands of miles of open ocean using stars and waves and seabirds to guide them, settling distant archipelagos from Hawaii to New Zealand. These journeys took weeks to months and were genuinely dangerous, but they succeeded through accumulated knowledge and careful planning. Later exploration became more organised and purposeful. The European age of exploration in the 15th to 18th centuries sent ships around the world, mapping coastlines, establishing trade routes, claiming territories. These voyages took months to years. Magellan's circumnavigation, the first to circle the globe, took 3 years and cost most of the crew their lives, including Magellan himself. But it proved Earth was round and measurable, that the oceans were navigable, that distant lands could be reached and returned from. The exploration of Antarctica came later, in the 19th and early 20th centuries, driven more by scientific curiosity and national prestige than by practical benefit. Reaching the South Pole required overland journeys across glaciers and ice sheets, in extreme cold, dragging supplies by sled, facing scurvy and frostbite and starvation. Roald Amundsen reached the pole in December 1911 after a journey of several months. Robert Falcon Scott reached it a month later and died on the return journey with all his companions, beaten by weather and exhaustion and bad luck. These expeditions were difficult and dangerous, but they were achievable with the technology of their time. They stretched human endurance and logistics, but remained within the realm of possible. And they contributed to our understanding of Earth's geography and climate, to the mapping of the planet, to the accumulated knowledge that now seems so basic and complete. Space exploration fits into this tradition. We're venturing beyond our home world into environments that are hostile and alien, using technology to overcome our biological limitations, accepting risks for the sake of knowledge. The timescales are longer now, the distance is greater, but the fundamental motivation remains similar. We want to know what's out there. We want to understand our cosmic environment. We want to push the boundaries of what humans can achieve. The difference is that space exploration is largely robotic. We send machines instead of people, at least for now, because machines can survive conditions that would kill humans, can travel for years without food or air, can be designed specifically for the environments they'll encounter. This is practical and sensible, but it changes the nature of the achievement. There's less immediate human drama, less visceral danger, less of the hero's journey that characterizes traditional exploration narratives. But there's still achievement, still discovery, still the expansion of knowledge and capability. The engineers and scientists who design and operate these missions are explorers in their own right, even if they never leave Earth. They're navigating through orbital mechanics and communication delays, solving problems in real time despite light-hour lags, guiding spacecraft through encounters with worlds they'll never visit personally. It's a different kind of exploration. More intellectual and technical, but exploration nonetheless. Beyond that, who knows? Perhaps permanent settlements on Mars or the Moon. Perhaps mining operations in the asteroid belt. Perhaps crewed missions to Jupiter's moons or Saturn's Titan, though those remain difficult to imagine with current or near-future technology. Perhaps interstellar probes, tiny spacecraft accelerated to a fraction of light speed, reaching nearby stars within a few decades of flight time, sending back data from exoplanets orbiting other suns. Or perhaps we'll focus inward, on understanding and preserving Earth, on solving the problems here before we spread outward. Exploration isn't inevitable. It's a choice each generation makes based on its values, resources, and priorities. The fact that we can explore doesn't mean we will, not indefinitely, not without renewed commitment. But the impulse persists, the curiosity about what lies beyond our current reach, the desire to understand our place in the larger cosmos. As long as that impulse exists, as long as we look up at the night sky and wonder what's out there, exploration will continue in some form, at whatever pace and scale we can sustain. Which brings us to contemplate what it all means, this patient journey across distances that dwarf human experience, this investment in knowledge that accumulates across generations. One of the unexpected gifts of space exploration has been perspective, the ability to see Earth from a distance, to view our homeworld as an object in space rather than the entirety of our existence. This perspective, sometimes called the overview effect, has profoundly influenced how we think about our place in the cosmos and our responsibilities to each other and to the planet. The first humans to see Earth from a distance were the Apollo 8 astronauts in December 1968, orbiting the Moon on Christmas Eve. As they rounded the lunar far side and Earth came into view above the Moon's horizon, they saw our world as a small, blue and white sphere against the blackness of space, isolated and beautiful and fragile. The photograph they took, called Earthrise, became one of the most influential images of the 20th century, credited with helping launch the environmental movement by showing Earth as a finite, unified whole rather than an unlimited expanse. The astronauts themselves were moved by the sight. Bill Anders, who took the photograph, later said, "We came all this way to explore the Moon, and the most important thing is that we discovered the Earth." Frank Borman described Earth as the most beautiful, warm, living object I've ever seen. The experience changed their perspective, made terrestrial concerns seem smaller and more manageable, emphasized the unity of humanity sharing a single delicate world. Later, astronauts reported similar experiences. The view of Earth from the International Space Station, orbiting every 90 minutes, shows the planet in constant motion, sunrise and sunset every orbit, weather systems swirling across continents, city lights marking human presence. Astronauts describe a feeling of connection to all life on Earth. a recognition that national boundaries are invisible from space, that the atmosphere protecting us is a thin, fragile shell, that we're all sharing one small world in an otherwise empty void. This perspective extends to the robotic spacecraft we've sent outward. Voyager 1, as it left the planetary realm in 1990, turned its camera back toward the Sun at the request of Carl Sagan, and took a series of images of the solar system, the so-called family portrait. Earth appeared in one of these images as a pale blue dot, a single pixel suspended in a sunbeam, barely visible against the vastness of space. Sagan's reflection on this image has become famous, a meditation on the significance and insignificance of human existence. He wrote about how everything that has ever happened in human history, every war and love story and triumph and tragedy, occurred on that tiny pixel, that mote of dust caught in the light. The perspective is simultaneously humbling and affirming. We are small, yes, but we are also capable of understanding our smallness, of sending cameras billions of miles to look back at ourselves, of reflecting on what we see. This perspective matters because it influences how we think about terrestrial concerns. Conflicts that seem overwhelming from the surface appear different from space. Political boundaries are human constructions, visible only through their effects, not inherent features of the planet. The biosphere is unified, interconnected, subject to processes that transcend national control. Climate, ocean currents, migration, disease, resource depletion, these operate globally, and addressing them requires cooperation and long-term thinking. The exploration of other worlds reinforces Earth's uniqueness. We've found no other planet in the solar system that's habitable without technological support. Mars is cold and dry with a thin, toxic atmosphere. Venus is hellishly hot with crushing pressure. The outer moons might have subsurface oceans, but their surfaces are frozen, airless wastelands. Earth, with its breathable air and moderate temperatures and abundant water, is remarkable. We evolved here, adapted to these specific conditions, and no other world offers them naturally. This makes Earth precious, irreplaceable in any practical sense. We cannot simply move to another planet if we ruin this one. Mars and the Moon might support small technologically dependent outposts, but they cannot absorb billions of people. Earth is our home in a fundamental way that no other place can be. Not in our lifetimes, not for many generations, even if we pursue colonization aggressively. The long journey times to other worlds emphasize this. 6 months to Mars is not a trivial commute. You can't evacuate Earth's population to Mars. You can't ship food back if crops fail here. Earth and any potential off-world settlements will be largely isolated from each other, connected by slow communication and infrequent transport, each dependent on its own resources and resilience. This doesn't mean we shouldn't explore or settle other worlds if we choose to, but it does mean we shouldn't see it as an escape from terrestrial problems. The challenges we face on Earth, environmental degradation, resource depletion, social conflict, these will follow us wherever we go. Mars won't be easier. Living in domes, breathing recycled air and growing food in hydroponics while radiation batters the surface is harder than fixing problems on Earth. If we can't sustain civilization here, where conditions are naturally favourable, we're unlikely to succeed in places that are inherently hostile. So the view from above, the perspective gained from seeing Earth as a planet among planets, as a small world in a vast cosmos, reinforces both the value of what we have and the responsibility to maintain it. We're lucky, extraordinarily lucky, to exist on a habitable world, and that luck doesn't extend to having backup options nearby. We have this one world, at least for the foreseeable future, and we need to care for it accordingly. The spacecraft we send outward, the long journeys they undertake, the images they return, all contribute to this understanding. This expanded perspective that includes both Earth's fragility and its central importance to us, this recognition that we're part of something much larger that doesn't particularly care about our survival, but also doesn't prevent it, leaving us free to choose our own fate. Let's hold this image of Earth from a distance, a pale blue dot in the cosmic dark, and think about what we're learning about worlds beyond our solar system. If we accept that interstellar travel is extraordinarily difficult, perhaps impossible with current or near-future technology, what possibilities remain for the very long-term future of exploration? What journeys might our descendants or our robotic ambassadors undertake if civilization persists and technology continues to develop over centuries? The most ambitious proposals involve generation ships, spacecraft large enough to support populations over multiple generations, travelling at a fraction of light speed toward nearby stars. The journey to Alpha Centauri, even at 10% of light speed, would take 44 years. At 1% of light speed, more achievable with conceivable propulsion systems, it takes 440 years. The people who launch would not arrive. Their great-great-great-grandchildren would. This raises profound questions about ethics and identity. Is it morally acceptable to commit unborn generations to life aboard a spacecraft, denying them the choice to turn back or change course? How do you maintain social cohesion and purpose over centuries, keeping the mission on track when those making the journey never chose it for themselves? How do you preserve knowledge and culture and the original mission goals across dozens of generations? Science fiction has explored these questions extensively, and the challenges are formidable. But some argue that if humanity's long-term survival requires spreading beyond Earth, beyond the solar system, these challenges must be faced. A single catastrophe, natural or self-inflicted, could end terrestrial civilization or even all life on Earth. Distributing humanity across multiple worlds, even multiple star systems, provides redundancy, insurance against existential risk. An alternative to generation ships is suspended animation or cryogenic preservation, freezing colonists for the journey and reviving them upon arrival. This technology doesn't currently exist for humans, though some organisms can survive freezing. If it becomes possible, it would eliminate the need for self-sustaining multi-generation populations aboard the ship. The journey time wouldn't change, but the subjective experience would collapse to moments, asleep at departure and waking at the destination decades or centuries later. Artificial intelligence and robotics offer another path. Instead of sending humans, send advanced AI systems with the ability to explore, learn, perhaps even construct new AI or robotic systems upon arrival using local resources. These machines could explore exoplanets, return data to Earth across the light years, and continue operating for centuries or millennia without the biological limitations that constrain human exploration. This approach has the advantage of being more feasible with current technological trajectories. We're already sending increasingly sophisticated robots to explore the solar system. Extending that to interstellar distances is an engineering challenge, but perhaps not a fundamental impossibility. The disadvantage is it's not human exploration, not settlement, not the establishment of new human civilizations among the stars. It's knowledge gathering, important and valuable, but different from the expansion of human presence. Then there are more speculative concepts that push the boundaries of known physics or require technologies we can barely imagine. Laser sails accelerated to a significant fraction of light speed by Earth-based or space-based laser arrays could reach nearby stars in decades rather than centuries. Breakthrough Starshot, a current research initiative, proposes exactly this for tiny probes weighing only grams, accelerated to 20% of light speed, reaching Alpha Centauri in about 20 years. Such probes would flash past their targets at incredible speed, gathering data for hours at most, and continue into the void. There would be no slowing down, no orbiting, just a high-speed flyby. But the data returned, transmitted back to Earth over 4.2 years, would be humanity's first close-up look at another star system. First measurements of an exoplanet's atmosphere and surface, first evidence of whether life exists beyond our solar system. If the concept works, if the engineering can be solved, a fleet of such probes could be launched toward many nearby stars over decades, creating a network of interstellar observations, each probe contributing a piece to our understanding of the galactic neighbourhood. The journey times, 20 to 50 years depending on distance and target, are long by human standards but manageable within a career or lifetime. You could launch a mission as a young scientist and receive the results as a senior researcher approaching retirement. Even more speculative are ideas involving manipulation of space-time itself. Warp drives that contract space in front of a ship and expand it behind, allowing faster-than-light travel without actually moving through space faster than light. Wormholes that create shortcuts between distant points. Or other concepts that remain firmly in the realm of theoretical physics and science fiction. None of these have been demonstrated to be possible, and most physicists believe they would require exotic forms of matter or energy that may not exist. But the equations of general relativity allow them under certain conditions, so they're not quite impossible, just far beyond anything we currently understand how to achieve. What's interesting about all these proposals, from generation ships to laser sails to warp drives, is that they represent different time horizons and levels of technological optimism. Generation ships could potentially be built with significant extensions of current technology, but they require centuries. Laser sails are closer to feasible but still face enormous engineering challenges. Warp drives are purely theoretical, requiring breakthroughs in physics we can't currently foresee. And all of them, even the most optimistic scenarios, involve timescales and distances that dwarf what we've discussed for the solar system. The longest journey we've sent spacecraft on within the solar system is Voyager's ongoing passage through interstellar space, now 46 years and counting. The shortest conceivable interstellar journey is measured in decades minimum, more likely centuries, possibly millennia with current technology. This vast gulf between the achievable and the desired, between where we can go now and where we dream of going eventually, defines the human relationship with cosmic distance. We're confined to our solar system for the foreseeable future, and even within that confinement, the planets are years away, the outer reaches a decade or more. Beyond that lie the stars, beautiful and unreachable, tantalizingly close on astronomical scales, but impossibly distant in practical terms. And yet, we plan. We dream. We calculate trajectories and design spacecraft and propose missions that our grandchildren might complete. Because that's what exploration is, pushing toward the next horizon, even when the horizon recedes faster than we approach, even when the journey seems impossible, even when patience is measured in generations rather than years. Let's rest with that for a moment. The image of future spacecraft, perhaps centuries from now, perhaps carrying humans, perhaps carrying intelligent machines, perhaps something we can't yet imagine, slowly crossing the light years toward other stars. And think about what this says about hope and purpose. After all this exploration of distances and travel times, after understanding the months to Mars and years to Saturn and decades to the stars, it's worth asking a fundamental question. Why do we reach for distant worlds at all? What drives this impulse to explore, to send machines and perhaps someday ourselves across vast gulfs of space and time? The practical justifications are often offered first. Space exploration drives technological innovation, developing solutions to extreme challenges that find applications on Earth. Weather satellites, GPS, telecommunications, materials science, medicine, all have benefited from space technology. Studying other planets helps us understand Earth better, particularly regarding climate and geology and planetary evolution. The economic potential of asteroid mining or space-based solar power or tourism might justify investment in the future. These are real benefits, measurable and valuable, but they don't fully capture why we explore. The cost-benefit analysis of sending a probe to Pluto doesn't obviously favour the mission, if judged purely on practical return. 9.5 years and hundreds of millions of dollars for a few hours of data from a small, frozen world far from Earth. The knowledge gained is scientifically valuable, but it doesn't cure disease or feed the hungry or solve immediate terrestrial problems. And yet, the mission felt important when it succeeded. People who had no direct stake in planetary science celebrated when New Horizons sent back the first clear images of Pluto. The images circulated widely, were featured in news coverage, generated genuine public excitement. Something about seeing a distant world up close, about extending human presence and understanding to the edge of the solar system, mattered to people beyond the scientific community. This suggests deeper motivations. Humans are curious by nature. We want to know things, to understand how the world works, to explore what's beyond our immediate experience. This curiosity is intrinsic, not derived from practical necessity. Children ask why, not because they need the information for survival, but because they're genuinely curious. That impulse persists into adulthood and scales to civilizational projects. We explore space for the same reason we climbed Everest, crossed Antarctica, mapped the ocean floor, and built particle accelerators, because there are questions we want answered, places we want to see, phenomena we want to understand. The exploration itself is the point, the knowledge the reward, the expanding of human comprehension, the justification. There's also an element of transcendence, a desire to connect with something larger than our daily concerns. Space is vast and ancient and beautiful in ways that inspire awe. Looking at images of Saturn's rings or the pillars of creation or galaxies billions of light years away evokes feelings of wonder and humility, a recognition of our smallness and the cosmos's grandeur. These feelings are intrinsically valuable, enriching human experience in ways that are hard to quantify but deeply meaningful. Exploration also represents hope, a belief in the future and the possibility of progress. When you launch a mission that takes 12 years to reach its destination, you're implicitly betting that the future will exist and will be interested in what you discover. This is an optimistic act, a refusal to accept that the present is all there is, an investment in continuity and growth. In a world that often feels overwhelmed by immediate problems and existential risks, space exploration stands as a counterpoint, a reminder that we can still do hard things, still commit to long-term projects, still reach beyond our current limitations. It's affirming in a way that transcends the specific scientific findings, affirming of human capability and ambition, and the stubborn refusal to accept boundaries as permanent. There's also a spiritual dimension for some, though it's often expressed in secular terms. The cosmos inspires contemplation about existence, meaning our place in the universe. Religious and non-religious people alike find space awe-inspiring, a source of reflection about ultimate questions. The Hubble Deep Field images showing thousands of galaxies in a tiny patch of sky, each containing billions of stars, each potentially hosting billions of planets, evoke thoughts about infinity and eternity and the nature of being. For some, this connects to traditional religious belief, seeing the cosmos as creation, evidence of divine grandeur. For others, it's a more philosophical or aesthetic response, wonder without theology, appreciation for existence without assigning it purpose beyond itself. But both responses involve similar feelings, a sense of encountering something vast and profound that puts everyday concerns in perspective. And there's the simple fact that humans are a restless species. We migrated out of Africa, across every continent, to remote islands and frozen tundra and deserts and jungles, always moving, always exploring, always wondering what's beyond the next horizon. This restlessness is built into us, encoded in our history and perhaps our biology. Space is simply the latest horizon, the newest frontier, the place we haven't fully reached yet. Some worry that this restlessness is dangerous, that it drives conquest and exploitation, that will carry our conflicts and destructive tendencies into space. This is a legitimate concern. History shows that exploration often precedes colonization and exploitation, and there's no reason to assume space will be different. We'll bring our problems with us wherever we go, along with our virtues and our knowledge. But exploration doesn't have to lead to conquest. We can choose to explore with respect and care, to learn without dominating, to value what we find without needing to possess it. The fact that we've often failed to do this in the past doesn't mean we can't succeed in the future, and robotic exploration, which dominates current space missions, inherently avoids some of the worst aspects of historical exploration because there are no indigenous populations to displace or exploit on airless moons and barren planets. Ultimately, we reach for distant worlds because we're human, and reaching is what we do. We ask questions and seek answers. We wonder what's out there and build machines to find out. We accept years-long journeys and decade-spanning projects because the knowledge gained matters to us, because expanding understanding is intrinsically valuable, because we refuse to be confined by the limitations of our current reach. The fact that Mars takes 6 to 9 months and Saturn takes 7 years and Pluto takes a decade doesn't stop us. It just means we're patient, we plan carefully, we commit to timescales longer than immediate gratification allows, and in that patience, in that commitment, we demonstrate something essential about human nature at its best: the capacity to work toward goals beyond ourselves, to value understanding for its own sake, to reach toward what we cannot yet grasp and keep reaching even when the grasping takes years. Let's hold that thought, the idea that exploration is intrinsic to who we are, and begin moving toward rest. As we approach the end of our journey together through the solar system and beyond, it's worth reflecting on the fact that the exploration we've discussed is ongoing, that the missions launched years ago are still travelling, still transmitting, still expanding the boundaries of human knowledge and presence, and new missions will follow, continuing a tradition that has no clear endpoint, an eternal journey outward into the cosmos. Voyager 1 and 2 are now in interstellar space, over 15 billion and 12.5 billion miles from Earth respectively, farther than any human-made objects have ever travelled. They're moving outward at about 35,000 miles per hour, covering about 300 million miles every year. In 10,000 years, they'll have travelled roughly 3 trillion miles, about half a light year. In 40,000 years, they might pass within a couple light years of nearby stars. In a few million years, they could cross paths with other stars entirely, wandering the galaxy as ambassadors from a civilization that may or may not still exist. They carry golden records, phonograph discs with sounds and images from Earth, greetings in dozens of languages, music from different cultures and eras, photographs of people and landscapes and scientific diagrams. The records are enclosed in protective aluminum jackets with symbolic instructions for how to play them. Their messages in bottles, cast into the cosmic ocean, intended for any intelligent beings who might find them long after we're gone. The likelihood of the records ever being found is vanishingly small. Space is vast and empty, and the Voyagers are tiny objects moving through it. But the gesture matters, the declaration that we were here, that we wondered about other minds in the universe, that we reached out across the void with hopes of connection. Even if the message is never received, it was worth sending. New Horizons continues outward as well, currently about 5.3 billion miles from Earth, travelling at 32,000 miles per hour. Its primary mission is complete, but it continues to take measurements of the space environment, the particles and fields that fill the outer solar system. Eventually, in the 2030s, its power will fail and contact will be lost. But like the Voyagers, it will continue moving, coasting through space long after it falls silent. These spacecraft represent humanity's farthest reach, the most distant extensions of our curiosity and capability. They're pioneers, not in the human sense of settlers establishing new homes, but in the sense of going first, of venturing into unknown territory and reporting back what they find. And they're patient, designed to function for decades, built to survive in an environment that's hostile and remote and unforgiving. Back in the inner solar system, other spacecraft continue their work. Mars rovers drive across ancient lake beds, studying rocks, searching for signs of past life. Orbiters circle Jupiter and Saturn, making long-term observations of giant planets and their complex moon systems. Probes are on their way to asteroids in Jupiter's Europa and Saturn's Titan, journeys that will take years but promise new discoveries. And on Earth, scientists and engineers plan future missions, designing instruments, calculating trajectories, proposing destinations. Some of these missions will be approved and funded and launched. Others will remain concepts, ideas that never quite make it through the competitive process. But the planning continues, the dreaming persists, the conversation about where to go next and what to learn never really stops. This ongoing nature of exploration, this continuity across decades and generations, creates a kind of immortality for the endeavour, if not for the individuals involved. Individual missions end, individual careers conclude, individual spacecraft fall silent. But the program continues. New missions replace old ones. New scientists take up the work of retired ones. New spacecraft venture to places previous craft only glimpsed in passing, and the knowledge accumulates, building on itself, creating a comprehensive understanding that no single mission could provide. What we know about Mars comes from dozens of missions over 60 years. What we know about Jupiter comes from multiple flybys and long-term orbital observations. Each mission adds detail, refines understanding, answers questions and raises new ones. This incremental progress can seem slow, frustrating to those who want dramatic breakthroughs and rapid advancement. But it's also reliable and sustainable, building a foundation of knowledge that supports more ambitious future efforts. You can't send humans to Mars safely without first understanding the environment, the risks, the resources available. The robotic missions going there now, taking 6 to 9 months each time, are gathering that understanding, preparing the way. And maybe that's the right rhythm for exploration, this measured pace of learning and planning and launching, accepting the years required for each step, being patient with the process. Space is not going anywhere. The planets will still be there in 100 years, in 1,000 years. We can take our time, do things carefully, build knowledge generation by generation. This doesn't mean we shouldn't also push boundaries, attempt ambitious missions, take risks that might fail but could yield extraordinary results if they succeed. Both approaches have value, but the foundation of careful, systematic exploration provides the basis for those ambitious leaps, the knowledge that allows us to attempt the improbable with some reasonable hope of success. And so the journey continues, outward and ongoing. A permanent feature of human civilization as long as civilization persists and maintains the interest and resources to explore. The spacecraft launched this year will take years to reach their destinations. The spacecraft launched next decade will reach theirs in the decade after that. The pattern repeats, each mission adding to our understanding, each journey testing our patience and rewarding it eventually with knowledge. We are, as a species, in the early stages of cosmic exploration. We've barely left our home world, visited only a handful of the thousands of worlds in our solar system, sent only a few fragile machines beyond the planets, into the vastness beyond. What we've learned is remarkable, but it's only the beginning. The true exploration, the full understanding of our cosmic neighbourhood, and perhaps eventually our galactic neighbourhood, will take centuries or millennia if it happens at all. But it's a journey worth undertaking, this slow expansion outward into the cosmos, this patient accumulation of knowledge about other worlds and the distances between them. It's a journey that defines us, that demonstrates our best qualities, curiosity and persistence, and the willingness to work toward goals that transcend individual lifetimes. And so we continue, launching our spacecraft, waiting years for them to arrive, receiving their data and images and measurements, learning about distant worlds one slow journey at a time, reaching outward even when the reaching takes longer than we'd like. Patient because patience is required. Hopeful because hope makes the wait bearable. Curious because curiosity is who we are. Let that image rest with you now, the ongoing journey, the spacecraft moving through the darkness, the knowledge slowly accumulating, the future unfolding one patient year at a time. Thank you for staying with me through this entire journey. We've travelled together across the solar system, world by world, understanding the months and years required to reach each one. 2.5 hours we've spent together, drifting slowly through distances that dwarf human experience, contemplating travel times that measure in fractions of lifetimes. I'm grateful you chose to spend this time here, letting these thoughts unfold at their own pace. From Mercury, where the journey is surprisingly hard despite its proximity, to Venus, our toxic twin reachable in months, to Mars, the accessible dream 6 to 9 months away, we've explored the inner solar system. Then outward to Jupiter, 5 to 6 years distant, and Saturn with its magnificent rings, 7 years from Earth. Farther still to Uranus and Neptune. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. Farther still to Uranus and Neptune, the ice giants requiring a decade or more to reach, and finally beyond to the Kuiper belt and the edge of interstellar space, where Voyager 1 and 2 drift outward into the cosmic dark after journeys measured in decades. The answer to our original question, how long does it take to reach every planet, is complex and beautiful in its complexity. It depends on when you launch, what trajectory you take, whether you use gravity assists, whether you want to orbit or just fly past. But the fundamental truth is simple. Space is vast. The distance is enormous, and patience is not optional. It's the price of exploration. And we pay it willingly because the knowledge gained justifies the wait. Perhaps the deeper answer is that the journey itself matters as much as the destination, that the years spent travelling teach us patience and perspective, that the achievement means more because it's difficult. We reach Mars in 6 to 9 months, and that's remarkable. We reach Saturn in 7 years, and that's an extraordinary demonstration of human capability and commitment. We send spacecraft to the edge of the solar system and wait more than a decade for them to arrive, and when they do, when the images finally come back across the light hours, the wait is forgotten in the wonder of discovery. Wherever you are in the world right now, listening to this as you drift towards sleep, I hope you're comfortable. I hope your breathing has slowed and deepened. I hope the tensions of the day have released from your shoulders and back and jaw. I hope your mind has quieted, occupied with images of distant worlds and spacecraft moving through darkness, patient machines on patient journeys, exploring on our behalf. If you can, imagine looking up at the night sky. Find Mars, if it's visible, a reddish point of light among the stars. That light left Mars minutes ago, travelling at the speed of light across the gulf between worlds. Spacecraft have crossed that gulf, taken months to do what light does in minutes, landed on that distant world and sent back images of rust-coloured deserts and ancient river valleys. Find Saturn if you can, a bright steady light among the wandering stars. Cassini circled there for 13 years, studying the rings, discovering fountains of ice erupting from Enceladus, watching storms the size of Earth rage across the planet's atmosphere. The journey took 7 years, but the destination rewarded the wait. All those worlds out there, orbiting the sun in their ancient paths, moved by gravity into dances that have continued for billions of years, and we've sent pieces of ourselves to visit them, to understand them, to bring their images and measurements back to Earth where we can contemplate them. The travel times don't diminish the achievement, they define it. Anything easy isn't worth celebrating. The difficulty makes it meaningful, and perhaps this is true of all worthwhile endeavours, not just space exploration. The things that matter take time. Understanding develops slowly, wisdom accumulates gradually, relationships deepen over years, not days. We live in a culture that often demands immediate results, but the most valuable things in life, knowledge and wisdom and deep connection, require patience. The universe teaches us this if we listen. The planets are years away and we reach them anyway, accepting the time required because the destination justifies the journey. So sleep well tonight, knowing that while you rest, spacecraft are travelling. Voyager 1 and 2 are moving outward at 35,000 miles per hour, adding 300 million miles to their distance every year, carrying messages from humanity into the cosmic ocean. New horizons, coasts beyond Pluto, measuring the space environment, transmitting data across billions of miles. Perseverance drives across Mars, collecting samples that might return to Earth in the 2030s. And new missions are being planned, designed, built, preparing for launches that will send them on journeys measured in years, continuing the tradition of patient exploration. You're part of this too, in your way, by being curious, by wondering about other worlds, by listening to this story. You participate in the collective human project of understanding. The knowledge we gain from space exploration belongs to everyone, enriches everyone, expands the human story to include not just our world but our solar system and eventually, perhaps, the galaxy beyond. Dream of distant worlds if you dream at all tonight. Dream of spacecraft travelling through darkness. Dream of rust-coloured deserts on Mars and methane lakes on Titan. Dream of Saturn's rings catching sunlight 400 million miles from Earth. Dream of Neptune's blue clouds and Uranus rolling sideways through its orbit. Dream of the journey, the patient years between launch and arrival, the slow accumulation of distance and knowledge. Good night. Rest well. Let your mind drift among the planets, contemplating the distances and the journeys and the remarkable fact that we've crossed them, that we continue to cross them, that we'll keep reaching outward as long as curiosity persists and patience endures. Sleep well. And know that the cosmos waits, patient and vast, full of wonders we're only beginning to understand.